Okay, so welcome back. First thing on Sunday morning, and let's get going with some physics. So this is now going to be slightly different style of talk, less of the mathematics compared to the last two lectures I gave, and a bit more of an overview. The emphasis now ends up being on cold atoms and the radio frequency field effects, but I will try to make some comments about other things as well during the process. Just wanted to acknowledge here two of my recent PhD students, both have graduated now, who contributed to some of the last two topics, which I hope I am going to reach if I have sufficient time to do that. And in the meanwhile, I think I should just get going. This was one of the things that motivated this piece of research that I'm discussing, so my personal involvement in it. I arrived in Sussex University in 1997, so a little bit like 1 year before this happened. And this was the local newspaper reporting on the physics experimental activity. We achieved the achievement of being the coldest place in the universe, briefly, for a very short period of time, exactly 1 second. Of course, other people in labs were doing this around the world, but it was a very exciting time. We were at Sussex. I was not involved in that experiment, I should say, although I was using the word we then. So the team who did this then, described here as icemen, because of the very low temperatures that we've been talking about, managed to achieve this, and it was getting quite exciting at that point in time. And when I looked at the experiment, this was part of the experiment over here. And you can see the vacuum chamber over here. If you don't know what you're looking for, it can be hard to recognize it. You just see a little bit of color if you're near the screen, which shows some of the coils that are involved in doing the magnetic trapping and also in making the magneto-optical trap, both of which are briefly described and we'll say a little bit more about here. This large box is just a pump, basically, to reduce the pressure inside the vacuum chamber here, because these kinds of traps and things will not operate at anything like normal pressures because of the effects of collisions, for example, by molecules in air. So during this process, there's something which is called evaporative cooling, which I'll mention later on. And the evaporative cooling involves radio frequency and sweeping radio frequency as a function of time, essentially chirping it, but it's really a controlled change in the radio frequency as time goes on, and it helps the final stage of making very cold atoms. And actually, it was when I was watching this piece of equipment, this very piece in the lab, that I started to get very interested in the controllability of these cold atoms with radio frequency, and that led on to many other things afterwards. This is not my name. I don't know who this is. Somebody's hacking into the presentation here. There we go. Okay. So we are regaining control from the hacker. Let's move on. So again, so this is the plan of the talk. Essentially, in the beginning, I'm going to talk or focus on the bubble aspects of things, and then move on to rings. And no, I don't want to make Graham co-host. Okay, thank you. And then we will discuss some of the very recent things that are out there, if there's sufficient time at that point. So basically, it's going to be bubble and then rings with different types of equipment. Now, I'm going to start with a sort of big overview, first of all, to emphasize, the versatility of things that can be done and are being done. So this is just a basic shell trap of the type that I described in the previous lecture, for example. This is a ring trap of the type that I described in the last lecture. And it's possible now to trap things within a ring or even on the surface of a ring, just like here we are on the surface of a bubble. And this is interesting for fundamental physics reasons as much as for potential applications. We've proposed, so these are done experimentally, We proposed double ring topology as something that's interesting for rotation sensing. And this is done with microwaves, and I will mention it later on. Experimentally realized are double shell traps. So if you have multiple radio frequencies, you can trap things in multiple layers, like a sort of onion business where you have onion skin layers of shells of things. And here we see that based on the we've proposed. So that's done experimentally. We've proposed lattices, not done experimentally. And there have been some very clever ring traps. So for the surface trapping on here, there's this arrangement which I shall mention, which is being done by Nottingham in the UK. And I will mention more about it later, so I shouldn't dwell on it here. I do mention these two reviews, which I flashed up in lecture 1, which give our overviews at different depths of the field back in 2016. So there have been developments since then, but this is a lighter level review, the JFIS-B one, and then much more technical details in this atomic, molecular, and optical physics review that came out in 2017 and is on the archive. And there's a stray symbol there, but I think if you ignore that, I thought I'd deleted that actually. Okay, so as I say, I'm doing a bit of an overview, especially here at the beginning, and focusing now for a moment on the ring business. This is just a list of points of interest for trapping on surfaces of bubbles so that you have the shell trap. So what are the points that are here? So matter wave interferences, especially if you allow the thing to collapse, you can cause a kind of implosion of these Bose-Einstein condensates. And that's very interesting. And it's a bit like something that was called a Bose-nova many years ago, which was the idea of a kind of exploding condensate. So collapse is of interest. Stirring them is of interest. Why is stirring them of interest? Because if you stir matter waves on these shell surfaces or anywhere, actually, you can create vortices. And if you create vortices, then vortex dynamics is a point of interest. And it's a point of special interest with these sort of bubble traps. Why is it a point of special interest there? Well, there is something called the hairy ball theorem in rather loose language, which says that if I if I model my head as a sphere, okay, physicists' model of my head, then if I try to comb my hair into a vortex at the top, sorry, I'm messing it up now, but anyway, if I comb it into a vortex at the top, and I have hair going all the way down under my chin and everything, you can't avoid having a vortex at the bottom. There's no way to comb it with a vortex up here and to avoid having a vortex at the bottom. So this is sometimes also called the hedgehog theorem or hairy ball theorem. So it means that unlike a flat surface, which is a place where people make 2D BECs, for example, on the surface of a sphere, vortices definitely have to come in pairs. And there's a lot of interest in realizing that and in understanding at what point you have to respect the topology of the sphere in having these vortices. So that's topological questions, vortices in bubbles. There's already some work out there on vortex dynamics on curved surfaces. It's a topic of academic interest. Already published back in 2019, interest in the condensation temperature in a different topology than being in a blob. Normally, when you make BEC, there's a condensation temperature, a point at which you get the collapse, maybe with some thermal atoms around in the background. And when you get that Bose-Einstein condensate, it happens at a particular temperature. And that temperature is modified if you're on a curved surface. So again, we are seeing topological effects on the property, which is condensation temperature. People are interested in tunneling between different shells. We're interested in this sphere as a sensor for microgravity, and we're interested in it as a potential place to do inertial sensing. So there's a very similar kind of trap to the shell trap that's used by Sackett in America for early stage rotation sensing. And you can make ring traps, which in a separate way can also be used for inertial sensing, and I will just touch on that quite exotically, I would say it's been considered that these bubbles can be used as a model of the expanding universe, and that's a published work in PRX. There's some pictures from it there. So what's attractive about that is that it's very easy to make the bubble bigger in principle, because if you remember how I described it all, it basically depends on where you have the magnetic resonance. You can change the position of magnetic resonance by changing the RF frequency. So it's a very simple tool to expand your bubble, to just increase the radio frequency, and you get a bigger bubble. And so you can make a model of something expanding. To model the universe, of course, is quite challenging. I'm not aware of detailed work on this at this point, but it's out there. So people are also interested in vibrational modes of bubbles and other things connected with that. So if we've been thinking about the future of this work at the moment, the filled bubbles. So bubbles are used on the Earth still. It's important, and there are interesting things that are happening even with the atoms at the bottom of the bubble field. But bubbles in space are one of the highlights that have attracted a lot more interest. And now that bubbles in space have been made, people are interested in doing it on Earth in these drop towers. So in Bremen and in Hanover, there are drop towers where they can drop a cold atom experiment, or even send it up and let it fall. So you get extra time in free fall. And people are thinking of doing experiments now in this equipment, which of course they could have done before, but they hadn't seen how interesting it was until the space station experiment. And now people are looking to other ways of making the bubble field. So for example, there's an idea to get a drop of one kind of BEC and then put a film of a different BEC around the drop, and make a shell system that way by having one thing on the surface of another flavor of BEC. And in fact, I'm also involved in work, I don't have a picture of it yet, to try and make a bubble field purely with optical forces, and not using radio frequency at all. And we wanted to see, how far we could get with that, and we're getting quite far with it. Okay, so we wrote a very recent review, published in 23, looking forward into what the potential futures are there. And you can read that to sort of see a future perspective look at how things might turn out. These, of course, are from the space station. This is the cold atom laboratory being installed in the space station. It's basically a module that they have to plug into the electricity and cooling systems and everything. And the rack goes in and they connect it up. And this was the astronaut that was heavily involved in installing it up there. And I'll just mention briefly, you don't know how much pain this image caused me with the publisher, because they are saying things like, well, this is an image of a human being. Have you got their permission to publish it? And so then I had visions that I had to write to this astronaut requesting permission. It didn't happen that way in the end. Apparently, just by going into space, the astronauts give permission for the use of their images, but I still had to demonstrate that to the publisher. So it was quite a lengthy process that took some months, in fact, to sort out. But there you go. So be careful about people in your images in publications. And right now, at the moment, there is a collection of papers. I think there's about 5 or 6 at the moment in a special issue, fully devoted to quantum bubbles in AVS quantum science, where quite a lot of cold atom work is currently getting published right now. Right, so I go back to the business of how to make bubbles and present it in a slightly less mathematical and more pictorial way. And I'm going to do that by using 2 methods. And this is a sort of picture of the usual setup of a magnetic trap. So with a magnetic trap, you usually want to have some trapping region. With the scheme called Yoffie-Pritchard, you can have a sort of local minimum like this, and you can kind of arrange that with the quadrupole traps if you add some plugging feature to be careful about the B field 0 at the center. So this probably is a picture that would apply more to the Yoffie-Pritchard type. There are other types of traps as well. but you have a minimum from the magnitude of the magnetic field at the bottom of the trap here. This is a spin 1 system, so there are 3 Zeeman levels, and you see the Zeeman shifting as you change the position here, which purely comes about from the magnetic field increasing. So that is a magnetic trap, and that is also a standard workhorse for cold atom physics. And a very standard thing to make the cold atoms in there colder, as I mentioned last time, is that you apply a radio frequency field here such that hotter atoms reach this magnetic resonance and then are transferred down to this potential and escape. And by preferentially taking away the hotter atoms, you cool the atoms that are left because the average energy goes down in the remaining sample. So that's called evaporative cooling using radio frequency. Now, what people didn't realize for a long time was that actually, if you make this radio frequency quite strong, then you essentially diagonalize the potentials with the coupling from the radio frequency. And when you diagonalize things, you may be aware you get avoided eigen values. You get, in terms of potentials, you get avoided crossings here. So this is the basic picture. This is the picture from the point of view of diagonalized or adiabatic potentials that we were discussing mathematically last time. So now in the region of resonance, you have a gap there, as we discussed, and at that gap point, you have a minimum in the field. You also have the original minimum of the field here. So this bit of potential mirrors this bit of potential, but where the resonance is, you have atoms located at these minima here. And that is basically the idea of the shell trap, that you have the atoms here. But you can see from that what was considered a little bit of a question in the early days. You know, we've basically moved atoms from here, where they would be made by the process of standard processes of cooling, to here, and this is on a completely different surface to where the atoms were originally, which is down here. So somehow you have to get the atoms from this location to this location, and that's basically called a loading procedure. And this outlines one of the ways of doing that. There are several options, in fact, nowadays, but this was the first one that was tried. So here's the original magnetic trap. And now instead of just suddenly turning on the RF field that will create the adiabatic potentials, you turn it on a little bit and shift the frequency. So as you shift the frequency of the RF, so you start below the resonance of the trap. So let me go back. That means that these arrows are too short and will not make a resonance here, or even here at the bottom. Okay, so they are below resonance. What you see is then a slight flattening of the field due to a little bit of interaction in this region. And then as you bring up the frequency of the radio frequency a bit, you start to get the shell trap. It starts very flat, like here, but then slowly gets its double well potential in cross-section. And as you increase the frequency even more, you end up with the target frequency that you wanted here. So just by chirping slowly and steadily the RF field up, you can convert the atoms, which always remain in the upper adiabatic potential here. It's always the top one, but almost magically, it's gone from being in the original magnetic trap to being in the radio frequency trap, and making the shell potential here, and having left this potential well through this chirping effect here. So it's a rather neat sort of way of transferring yourself from the center trap to the outside trap. So that way you can make a resonance eggshell. So we sometimes talk about eggshells, and this is an image that we made later, actually, for one of the review articles, which shows what the magnetic field is doing in a Joffre-Pritchard trap. So in Joffre-Pritchard, you have a predominant direction of the field. You see it curves, yes. You see the arrows pointing slightly different directions, but basically it goes in one direction. And that means then that in terms of applying the radio frequency, you can apply it in a perpendicular direction. And remembering that the perpendicular component of the RF is what counts, then you will get a strong coupling everywhere around the surface of the bubble field. But it can vary a slight amount depending on how steep these angles are at the bubble surface. Now, I often talk about dressed traps. It's just the same thing as this radio frequency trap, and we talk about radio frequency dressing. So I just mentioned briefly Cohen-Tanuji again. So Cohen-Tanuji was involved in this paper back in 1977, which was about a picture of resonance fluorescence based on the dressing model. And essentially, he was doing the same kind of dressing that I'm talking about, applying, in this case, not RF, but an optical field. And when he does that, he gets, this is like a two-level atom, he gets these pairs of energy levels, a little bit like the Jaynes-Cummings energy levels, which go up in a ladder. In his case, unlike our case, he also had spontaneous emission. Now, we are not going to have spontaneous emission with the radio frequency, although we want spontaneous emission with the laser cooling step, as we discussed. That was important there. But with radio frequency and also with microwaves, the frequency is so low, you don't really get any spontaneous emission for transitions of that frequency. And that's because of this omega cube or frequency cube dependence that I mentioned briefly in the last lecture. So because it's frequency cubed down in RF and microwave frequencies, essentially the spontaneous emission rate is zero. And that's important, for example, for long lifetime of microwave qubits in some quantum computing schemes as well, that you have this long lifetime. So we don't have the spontaneous emission here, but just to say that this dressing language comes really from Cohen-Tanuji's work, and then I think Cohen-Tanuji himself used this language from condensed matter physics, and it's got transported now. So this is now a second view of how the trap works. So here now we see a sort of linear behavior of the magnetic field with distance in one dimension. And what we have here is a magnetic resonance at this location. So this could be a section through a quadrupole magnetic trap. So this is like a Zeeman splitting, but because of the linear gradient in a quadrupole, we see the Zeeman splitting happening as a function of space, because the B field increases with space. This is the magnetic resonance here. And in this picture, you can just argue that, well, if there's an atom here, because of this gradient in the potential, the atom will just gently start rolling down this slope, and then it enters the magnetic resonance. If the resonance is strong enough, it's adiabatically transferred to the excited state, the most excited state in this bundle of three, and then it will, for a while, it will carry on up here, but eventually it'll turn around, it loses its kinetic energy, and then it will go backwards. And by repeating that process, it goes backwards and forwards, and it's basically then in a trap. The dressed point of view is to look at the adiabatic potentials that you have here. So you diagonalize this problem, as we had in the previous picture with the green lines, and then you see the trap directly, because for making this trap, you take this section of the bottom potential and you take this section of the top potential and you stick them together, basically, when you do the diagonalization. So that makes the trap at this point. So why have I got different ways of explaining it? It's because in the very beginning, it was difficult to persuade experimentalists that this could work. So some people thought it would not be possible to trap atoms at this location, because of the interactions with the radio frequency. And it turns out it is possible. And this particular diagram and argument was one way I found that it was easy to convince, or easier to convince experimentalists that it's worth having a go at it and doing it. And now it's taken off a bit. So this were the early results from 2004. So my goodness, nearly, just over 20 years ago now. And the first results made in Paris by the group of Helene Perrin for the bubble field. And what you see here is just a bit of curvature because the atoms are at the bottom of a very large bubble. So you see the effect of gravity here. In this image, you see a smaller bubble field, and it's like a rugby ball, the shape of the bubble here. And you see hot atoms. And you can almost see the outline of the field here, the atoms trapped in the bubble at the top at that point there. But those were the first published results on this thing, came from Paris. And this, in case you're interested, these are my photos of the Paris experiment. I took the photos a bit later when I was there. And actually, for some reason, I focused on this part of the equipment. The atoms are actually inside the magnetic fields here. This is a close-up of that. So these are what you see here is sort of copper, which is used for cooling everything because there are high currents. It can get quite hot, this particular experiment. There are additional coils around the outside here to compensate the Earth's magnetic field, to have full control of everything. And there is an RF coil hiding somewhere in here. There is an RF coil, and I remember this is the wire that goes in carrying the radio frequency, which is critical then for making the trap and for doing the evaporative cooling as well. So this is just the vacuum part. So I got criticized at some point by the people who worked in the lab here, who's pointed out, well, there's a whole load of optics here, and that's truly true, you know, like a table of optics that controls everything, and then is sent up with mirrors to the trap here. And of course, they are very proud of all that optics on the table there. But I was focusing here on the actual center of the trapping, the bit where all the action on the atoms is. So yeah, and this is then just to mention a much more recent experiment, which is to make the multiple shells. So these are double shells, which is done with 3 RF, and you can understand why it's 3 radio frequencies from using this diagram that we've just seen. And now I expand it to 3 frequencies. And if you follow the path of an atom here, you can see that a fast atom would be going downhill here, uphill here. So you have a trap here. Here, if it's going along the top, it's going uphill, and then it would go downhill. So this is an unstable point. And now if it's going down here, you have a trap formed here because it's going downhill and then uphill, and that's this trap here in the dress picture. So you have 3 resonances in order to make 2 traps in different places, and that was done by Chris Foote in Oxford in the UK. Okay, so a few words about the space station then. So it's a modular system where this cold atom laboratory, and it was actually done for space experiments. It was done on a very fast timetable. So originally planning started in 2012, and they were expecting the whole mission to end in 2020. It's still going on up there. They were expecting launch in 2017. I think the launch was actually in the middle of 2018, and the experiment went up. And actually, the bubble experiments were only one of about 10 types of experiment that they intended to do up there. So they had other experiments. For example, they wanted with 2 species of atom to compare, you know, how do atoms in microgravity, if you put some forces on them, how do they fall at different rates and things like this? You know, this experiment for comparing the behavior of atoms in what's left of the gravitational field or in other fields as well. And there were some other experiments, and but unfortunately the microwave part of the experiment broke, and they couldn't do many of the experiments. And with what was left, the bubble field was one of the things they couldn't do. So the experiment is here in this rack, right next to the astronaut exercise machine. So whenever I'm seeing live video of the space station, I can quickly locate this if I just see the exercise machine, because I know if you see the exercise thing, which is quite prominent, then you just look down here and you see the cold atom laboratory in that spot there. It's not good for the experiment if the astronauts are exercising, because it moves the space station very slightly as they are moving around. So they do these experiments when the astronauts are sleeping during the astronaut nighttime. These were some of the results from 2022. So this is an experiment to just fill the bubble field. Various parameters, you can see that they're making the bubble bigger and bigger as you go to the right of these images for different parameters. And you know, somebody was asking yesterday about shortcuts to adiabaticity. I don't know if you've all heard that, but at the moment to expand out to quite large bubbles. They use these shortcut methods, which are designed to expand quickly without getting a lot of oscillations as you expand outwards. It's a nice technique, but I won't go into that because of time. Then the other set of experiments over here shows results of collapsing the bubble. So you turn off the radio frequency dressing field and let the thing collapse on the magnetic potentials. And then you get these incredibly complicated patterns, which are quite, they're so complicated, it's quite tricky to analyze them. But you have a very interesting set of data there, which I think is keeping them busy looking at them. So this is a close-up of some of the bubbles. So as I pointed out last time, there's still some asymmetry in the bubble. This is a column density image, and to some extent that explains why you have these blobs on the edges here, because it's not a sphere. It has a rugby ball shape, and you have a bit of pooling of atoms then in terms of column density at the pointed ends, but nevertheless it's clearly asymmetric. And there are various reasons for that, but one of the reasons is to do with how the experiment was designed. So this is maybe I'll go ahead. No, oh, I thought I had a picture. Okay, here it is. So this is a picture of a core part of the experiment. So this is the vacuum chamber here. It's a commercial vacuum chamber. That was one of the ways that they were able to get this experiment up cheaply, relatively cheaply for space experiments, and also quickly, because they were trying as much as possible to use off-the-shelf electronics and components, including this vacuum chamber, which is made of glass. The vacuum chamber is here. You see it sort of tinted purpley. There is an atom chip on the top. It's essentially glued to the top of the glass, and it even replaces part of the glass at the top here. And there's a pattern of wires. You hardly see it here, but you can see a bit of gold color, which is the pattern of wires which forms the trap, and which is shown in detail on this picture here. So this is part of that pattern. This bend here, in combination with these straight line wires, is all you need to make a Yoffie-Pritchard trap from an atom chip. And it's important to have this kink. And the magnetic fields from these wires, with the currents going in the correct directions, will make that trap. And this is one of our own simulations of the atom chip and a cloud of atoms trapped above it here. Normally on Earth, you would trap underneath, and sometimes you get confused about the fact that on Earth, it's like in this picture over here, where you would have the atoms in the vacuum chamber underneath the chip. These circular components are the radio frequency coil and microwave coil, which are used to generate the radio frequency microwave. And these are the coils before installation. Here they are installed on the surface of the trap, and we modeled all the details of that. So we have a model of how the experiment works. We modeled what the atoms would do in that, and we could find similar asymmetries to the ones that are observed. And the cause of well, there are several causes of the asymmetries, but one cause of the asymmetry is the fact that in the experiment, the coils here are only on one side of the atoms. And if you have your atoms in the vacuum chamber at a point, that doesn't really matter. But when you have an extended field of atoms underneath, then you can suffer from the fact that if you're a little bit closer to the coils, the magnetic field is a bit stronger from the radio frequency. And if you're further away, it's a bit weaker. And that has an effect on the dressed potentials, the adiabatic potentials, which I thought we had a minute ago. Here they are, which means that, where it's stronger, you have a bigger avoided crossing. And this is part of the avoided crossing. We just show the top adiabatic potential here. And when the RF is weaker, if you go further out, even a little bit, we're talking about tens of micrometers here, then you have a weaker magnetic field and the crossing is closing up, and that puts the potential lower. So it's a lower potential on this side than it is on this side. And as a result, the atoms are pooling on one side of the on one side, and you get the asymmetry. There are other reasons for the asymmetry as well, but I won't get into that. So we decided that when the microwave coil would be working again, we could use a trick with the microwave coil to actually balance things back. So you can add in, it's a complication, but you can add in microwave dressing and use the fact that the microwave coil is very similar. And I've lost the picture of the coil. So it's a very similar kind of coil. And the same thing will happen, that if you are closer to the coil, the microwave is stronger. And if you're further away from the microwave coil, it's weaker. And now we try to get an opposite effect to rebalance the asymmetry by using an off-resonant dressing with the microwave coil as well. And this is just a list of theory papers involving microwaves, because we use microwaves as well. It's intrinsically part of the nonlinear Zeeman effect. We used it in this induction trap, in the lattice proposal, and so on in other works, but that's just the history of it. So when we apply the compensation, this is the best result here, where you see that the color is the same all the way around the cross section through the bubble here. And we had a good compensation using the microwave field. So the microwave was actually useful in the end in that case. Right. So some things to be aware of then. The surface variation of Rabi frequency creates a landscape. So that's what we've just been talking about. In general, you have to worry about zeros of coupling, but that just means being careful that you essentially aim to have the radio frequency field direction perpendicular to the static magnetic field direction. If you keep that situation good, then you will not get a zero of coupling of this kind. But in other setups, it can be a problem. And then surface variation in trapping frequency can also have an effect. There is a trapping frequency here. You can imagine that the atoms can vibrate in this harmonic well. That's like a kind of breathing motion that you can make on the surface of the trap. And curiously enough, that trapping frequency, if you quantize it, it's like the ground state. If you consider the ground state of the harmonic oscillator, that energy depends on the frequency of the oscillator. And then you have a problem if your frequency here, if your vibrational frequency here is different to the vibrational frequency here, then that means that the ground state energy, if it's higher here, the ground state energy is higher here compared to here. And that creates a force that will move the atoms around as well and create asymmetries. So that problem exists as well. One thing that is not a problem is lifetime on here. So originally people were worried, well, the atoms will not last long. So lifetimes even on Earth are at least 30 seconds is possible if you have a good vacuum, which is reasonable, very reasonable for these kinds of experiments. And what helps with the long lifetime is that Landau-Zenner is very effective. So here I go into a bit more detail on these things, and so I might go a bit fast to save a bit of time. The observation of this ground state energy creating a kind of force was something that we had back in 1999 with this publication on a different topic, which was looking at electron spin. And essentially what we had was a wave packet here being split in a Stern-Gerlach device. And it was meant to move upwards and downwards, but it's in a kind of potential. I think I added some lines to mention the potential here. So here we have the potentials that it's meant to move in. So it's a different piece of physics, but the thing that's common is that you have a potential here with a ground state energy, which is reducing as you go along this red line, because this harmonic oscillator is opened out more, so it's not as high a frequency as you are here. Very curiously, this wave packet, there's a picture of it here, this wave packet was meant to split, and half of it was meant to go up and half of it was meant to go down. But what actually happened was the one that should have gone up just stayed there and didn't move, and the one that went down was going too fast, at twice the speed it should have done. And why was that happening? It was precisely because these ground state energy was encouraging the atom to accelerate along this track, and the changing ground state energy, creating a force, was making this wave packet that wanted to go up there stationary by balancing the Stern-Gerlach effect, which was a very curious result, but makes you aware of what can happen on the surface of the bubble field if you have a variation in vibrational frequency. Now I'm going to discuss these points in detail, so I won't dwell on that slide. So first of all, then, as I mentioned yesterday, so maybe I can go fast, but here are the pictures. The nonlinear Zeeman effect is not an issue. So the linear Zeeman effect means that if you have an increasing magnetic field, then the space between these different Zeeman split states will increase linearly with the applied magnetic field. Not quite the same as distance here, but they are all marching together for small distances and small fields. When the field gets big, the separate resonances start coming in different places, and this is because of the nonlinear Zeeman effect, which happens with strong magnetic fields. And we looked at then the effect of that on the dressing, and these are the results, if you like, for the adiabatic potentials that show, in this case here, softening of the trap because of these different resonance points, which are marked with the dots here. So it softened it, it reduced the vibrational frequency. But on the other hand, if you would turn this upside down, which would happen with the f equals 1, so this is f equals 2 case, if you go upside down, then you have a sharpening here in this lower adiabatic surface, which becomes the upper adiabatic surface for f equals 1 case. So it can soften or sharpen either way, but we don't get a problem with the trap apart from that. As I mentioned, lifetime is not an issue. We discussed Landau-Zenner in the previous lecture, so I won't say more about that. And we had this equation involving the effective magnetic vector potential in the last lecture, so I don't discuss that. And I will go, I think to speed up, I will just flick over this, but this is the details of the calculation that looks from a point of view of eigenstates in the magnetic trap. It looks at calculating in detail the leakage rate of the trap and then comparing it to Landau-Zenner models over here. So that this leakage theory produces a leakage. So this is a decay rate in the trap as a function of Rabi frequency. So big Rabi frequencies are good because it's strong coupling, and Landau-Zenner is really fully operating. So the further you go to the right, the better the trap is here. And what we have comparison of here is essentially a wave packet analysis based on Fermi-Golden rule, in fact, for the residual decay rate, and a more precise treatment, which is giving us an estimate of the decay rate. And then we compare it to two types of Landau-Zenner treatment. I don't go into the details here, but there's one Landau-Zenner here, another one here. It all depends on which velocity you use in Landau-Zenner. And you see that these nicely bracket the actual results. And we tested that experimentally as well. So here we have an experiment where we actually weakened the trap. We made and it was difficult to do actually experimentally, but the RF amplitude was turned down to make the trap leaky, and then we measured the decay rate and checked how it compared with theory. But actually difficult to do that experiment. It's much easier just to have the trap on than to weaken it. Okay, and this is then what I briefly mentioned last time, the RF cooling of an RF trap. So here you see maybe the easiest picture to understand it in. We have here for F equals 2, the bare trap picture. So this is the magnetic trap here. And here we have resonance with the first RF, and also over here, of course. And here we have a resonance with a second RF over here with a higher frequency. So you can see two magnetic resonance points in that case. And what we do is we make the first RF much stronger and go to the dressed picture. And in the dressed picture, then we have the usual RF dressed traps here and here. So now we have a bubble field. And now this second resonance appears just to the left and to the right here. Notice it doesn't appear on the inside here, at least to a good approximation. It doesn't appear on the inside here and the inside here. That's due to the sort of detailed mathematics, but you see it already in this picture here. So then you can cool the trap, and this has been done because you have the same idea. You know, hot atoms in the dress trap here can reach this resonance point, which is a weaker radio frequency, so it doesn't make a dressing trap itself, and then the atoms escape and go down here. And so that's a way of cooling the trap. How effective that is needs, I think, a bit of further investigation. Some experimentalists are rather enthusiastic about it. Others say, well, you know, it may not be effective at cooling because you have this 2D surface thing and rethermalization. In evaporative cooling, you need rethermalization because you have now atoms in a non-thermal distribution when you evaporate things. And it has to rethermalize, and this happens more slowly with atoms spread out on a sphere, for example. But anyway, it was achieved experimentally. Okay, so let's go to the ring topology in the last minute. So there have been several schemes which use bubbles to make rings. We had an original proposal using standing waves of light. So blue detuned light in standing waves can repel atoms. I didn't go into that in the last lecture. I could have done, but it would have taken extra time to do the detailed theory of how that works. But it's a story that goes in parallel with the laser cooling story. So it's nice to include that story. But it's a non-dissipative potential. It's a conservative potential. So if you put on a blue detuned lattice of light here, you can trap things in layers. And if you combine that with the bubble trap, you end up making a ring trap. And in fact, this was realized in 2008 as one method of making a ring trap. Meanwhile, Chris Foote in Oxford did it a slightly different way by using a blue detuned light sheet. So instead of having a whole set of standing waves, he had a single, you know, on Earth, so you have gravity involved in this as well. He had a single sheet of blue light, which he brought up on the bubble from below, and that created the ring trap in his case by sort of pushing on the bottom of the bubble. And there have been atom-shaped methods proposed. I won't go into the detail of that. And this highly complex method, which is the one which, with adjustments, can be used for trapping on the surface of a toroid as well. So this is a proposal by Fernholz and collaborators, which involves a set of permanent magnets on a chip surface, so centimeter scale surface. I have an image in a minute. You have those permanent magnetic fields. You have RF antenna in rings above and below, phased so that you have a circular polarization of the radio frequency, but the axis of the circular polarization is changing as you go around the ring. So again, it's one of these complicated 3D geometric things. It's great fun, and this is being built as part of a proposal for Sagnac rotation sensor. In fact, this is some of his experimental results from last year, showing in this kind of trap atoms moving around in the ring. And for a Sagnac experiment, what he will want to do later on is get the atoms in a controlled way moving around the ring in opposite directions. and this makes it Sagnac interferometry. And then they look at what happens when the atoms meet at the back. They monitor that by looking, for example, at the population of atoms in the particular states that are available for the atom. And they can get information about rotation of the laboratory frame from doing that. So the other way of making rings that I mentioned is to do shaking of bubbles. And there are extraordinarily large rings made that way. I mentioned that last time. And you can also make tilted rings. And that can also be used for Sagnac interferometry, because these tilted rings then are a bit like buckets. And so you have two buckets of atoms in two different ground states, so the microwave separated ground states, and you have the tilted thing, and you're shaking the whole thing with RF and all of that sort of thing. And curiously, because of the different signs of the G factor that I mentioned, when you apply the necessary fields to rotate the tilt here, the different ground states go around in opposite directions. So it's perfect for Sagnac. So then they can get two tilted rings, and they go around in opposite directions, and then they can test what's happened to the phase when they meet at the back there. So that's another approach to Sagnac. Okay, so now I've reached some of my recent student work on this, but actually I would have liked to have jumped to our own Sagnac interferometer in this context, so I'm slightly out of order here. Anyway, I'll come to that eventually, because I have about 15 minutes left, I think, from that. This may not be something that you know. This is a piece of quantum optics, and it's, as I say here, Jansky's representation of a state in phase space. So it depends how much quantum optics you've done if you appreciate this. But what Jansky showed is that you can get the eigenstate of a harmonic oscillator, a Fock state, mathematically by taking a whole set of coherent states, so minimum uncertainty states, and planting them in a ring around a radius, which here is given by the magnitude of the coherent state parameter alpha. That gives the radius. So you put down a lot of these coherent states and put them down with the right phase factor, and you make a Fock state. Okay, and the Fock state, if you look at its phase space distribution functions, so the probabilities sort of as a function of momentum and position, they have a ring in phase space. That's a ring in the phase space. But then the question was, well, what about a ring in real space? Because we're interested in rings. And so here now, instead of having 1D position and 1D momentum, I think about putting coherent states in a ring in 2D space. So this is X and Y, not so it's not position and momentum, it's position and position. And I put down a ring of Gaussian, 2D Gaussian wave packets, and do the numerical and analytic calculations as far as can be done on that to see what we get. And it turns out that what we get is an extremely good approximation to the ground state of a ring trap, which is something that we're interested in. And the ground state of the ring trap then is closely connected to this, and that's useful because we don't have analytic formula. Well, we do now, but we don't have analytic formula for the behavior of the ground state of the ring trap. For example, if you let it go and let it freely expand. But we do have analytic formulae for how a Gaussian wave packet expands. That's extremely well known, how it expands in 1D or 2D or 3D. So because we are here taking a superposition of all these Gaussian wave packets to form the ring, we can understand how the whole thing expands just by looking at an individual Gaussian wave packet and then adding up all of the individuals together, an integration basically. And it's hard to do. Well, I think it can, yeah, I think it was done exactly, but it's complicated, and you can get some simple formulae out of it though. So what do we find out from that? From that we get an understanding of, well, if you get a millimeter-sized ring of coherent matter waves, what happens to it if I let go of it in a vacuum chamber? Okay, some people will be saying, well, it will just drop to the bottom because it's so big, nothing happens. Okay, so this gave us the formulae to understand, what will happen. These are the pictures for that. So this is on the left here. This is the expansion of the ring. And we see that we're taking a cross section through the ring. So you just see here 2 bits of ring, and eventually they expand. You create an interference pattern here, and we can find the details of that interference pattern now from this formula. And we did the same thing for the bubble by, in 3D, putting 3D Gaussian wave packets all around the surface of a bubble, and also getting a good approximation to the ground state there. How do we know it's a good approximation? Well, we calculated fidelities. So we calculated the fidelities of our approximation to the real numerical ground state of the system in 2D for the ring and 3D for the shell. And what you will see here is many nines fidelity. So these things work extremely well. So we're quite pleased with that. The only negative thing is that this is without interactions. So if you allow interactions between the atoms, then you should really solve something like the Grozbedievsky equation, which is a nonlinear equation. And that's not something that we know we can do with this method, unfortunately, not at this point anyway. So I'll whisk through that because of time. Okay, so this is the bit that I wanted to go to next, which is our interest in rings and things. So we've had a number of schemes for making waveguide loops. We can have them in this kind of double circle arrangement. We can have them in a perfect circle. This is our microwave induction scheme, and the original proposal was to put a large number of these inside a small vacuum chamber. So part of the quantum technology drive was making very small vacuum chambers, not these big pieces of equipment, but matchbox-sized vacuum chambers with good enough qualities and the source, a bit like that chip thing that I was showing, the laboratory on a chip idea. And we fabricated some of these things for testing, including the microwave antennas and so on. But I won't go into detail on that. So that's one approach that is very much close to my heart. Another approach is being taken by my collaborator, another collaborator in Paris, Carlos Garrido in CERT, and he's building a ring trap based on similar ideas of magnetic fields and radio frequencies. And this is a picture of his experiment before the magnetic shielding was put on. And that's also for the Sagnac effect. Now, I have a few brief comments here about, why do we want to do rotation sensing with these cold atoms, with these matter waves? Well, the point is that the matter wave wavelength at low temperatures is going to be so different to what the matter wave wavelength that you get with light. And in fact, the potential advantage that you can find by using matter waves is a power 10 to the 10, in fact, or a factor 10 to the 10 in sensitivity if you compare the two using light. So light is conventionally used, for example, in an aeroplane in optical fibers to make a rotation sensor. So you wrap the fiber around in a loop, and you monitor the light coming out, and you can see phase changes through the Sagnac effect, the rotation of this fiber bundle. And the proposal is to do the same thing with matter waves, and utilize this 10 to the power 10 advantage, which is a massive increase in sensitivity. And in fact, the philosophy is, or at least my philosophy in thinking about these things, is that it's so huge, you can afford to lose a lot of that sensitivity through not being able to make the best experiment. So not having a laboratory scale, room-sized experiment, but literally making something where it's inside a small vacuum chamber, which is the size of a matchbox with very small coils around it. And so it's a philosophy that also comes from that business of the chip scale atomic clock, where all of a sudden they were able to, well, I don't think it was that suddenly, but anyway, they were able to miniaturize an atomic clock from being this huge thing down to something which is like a size of a coffee bean or whatever. So same ideas going on here to make more sensitive rotation sensing. And why do we want to do that? It's because in a number of situations, people want to be able to navigate without using GPS, because GPS can be turned off, GPS can be spoofed. There have been cases where it's been spoofed near airports, and it's also being jammed in places like the Russian Eastern Europe boundary. There are jammings going on there, and the aeroplanes can't always use GPS. So navigation without GPS, also for submarines, they don't have access to GPS, or if you're in caves or something, you don't have access to GPS. So navigation without GPS is desirable, and for that you need more accurate rotation sensors and other aids to navigation, such as things that I discussed last time. You know, the fact that clocks in the gravitational field will change their frequency. This also can be used as an aid in navigation. So for various reasons, then, it's of interest to do it with matter waves. And for that reason, and I don't think I'm going to dwell into it much, I'm also studying with another student who's finished now, the detailed propagation of wave packets around rings, for example, which it turns out is not so simple. So, it's the wrong slide. Okay, this is the wrong slide. So here we see a real wave packet going around a ring. And if you look very carefully, you'll see that it's a bit sort of tilted. It doesn't follow the ring exactly. So there's a bit of tail here on the inside and a bit of tail here on the outside. And actually now we've figured out how to explain these dynamics, and we can approximate it. And that's done in a quantum optics way, using a sequence of translational, squeezing, and rotation transformations. That's what all this is down here. And we published that recently in a book. Okay. So I'm not going to say much to conclude. I'm a little bit over time, maybe. No, I may be bang on time, apart from the questions time. Just to say then, there is a lot of versatility in this combination of not just the conventional magnetic trapping, but adding in the radio frequency and maybe even microwave as well. A lot of applications people are interested in, especially the quantum technology applications. It's a subject that's ongoing, and these slides, I don't want to be there. So I just finish by acknowledging the collaborators. So in particular, those last slides that I was showing about the ring expansion and the propagation in the waveguide are due to the two recent PhDs who've graduated. And the strong link to the space station activities with Nathan Lombard in the States, but there are many other contributions that I've reported here by other people listed, and I thank them all, and I thank you for listening to the 3 lectures, because I think I've finished. Apart from any last questions, is there anything? Yeah.
What strength fields do like the nonlinear Zeeman effects?
What kind of strength? Because it varies from atom to atom, but we are talking maybe about the half Tesla to Tesla level. So quite strong. Strangely enough, it crossed my mind as I was talking about that. Yes.
Thank you. I missed the relation between circular sensing and GPS. navigation. How this is useful for?
How it's
How is this is useful for GPS navigation?
yeah, so it's useful if you don't have GPS.
Yeah.
So
yeah. So
the problem is, I mean, if we consider, for example, an extreme situation, but for example, in an aeroplane flying across the Atlantic from, say, Paris to Washington, D.C. So if that plane would not use GPS and just use the rotation sensor it has inside, and the other things as well inside the aircraft, which is standard equipment, then by the time it would get to the US, it could be hundreds of kilometers off from location, because these rotation sensors drift. And the drift will accumulate as time goes on, and you can get a huge deviation in location by the end of your journey on those scales. Now, in reality, that doesn't happen. It doesn't happen because they get updates from radio beacons or from GPS satellites, which put the location back to a good spot, and then the inertial sensor can tell them if they're maneuvering, what is happening on a short time scale. But if you don't have those beacons or GPS, if the GPS has been destroyed by some bad actors, they say in the language, then you don't have the things to relock to. You might be lucky and have some radio beacon, but anyway, you could have a problem without the GPS. And so then you want a more accurate rotation sensor, which will not drift as much on such a journey like that, or on maybe shorter time scales. And that's why you want to switch to Sagnac with matter waves, because, well, if or when it's demonstrated fully, I mean, it isn't at the moment, it's a research area. But the expectation is that by using this more accurate Sagnac, that you can then accurately go to a longer distance than you could with the conventional optical fiber approach and optics. Yeah, okay. So that's the connection. So people are worrying about GPS denied. How do you navigate when you don't have GPS? The GPS denied navigation. I should say that it has other interests. So there are some car manufacturers who are interested in this if it can be made cheap enough, because inside big cities, tunnels, places like this, you don't get a GPS signal for car navigation. The problem with big cities as well is that you have reflections of the GPS signal from buildings, and so it's not accurate. And so you could have some issues, for example, with self-driving cars and things like this, which would be undesirable. So, although they still sort of image what is happening in front, behind, and everything, but some car manufacturers are interested in navigation systems, which will operate when the GPS is a bit confused that way. Yeah.
Okay. Thank you.
Okay.
Yeah, if there's no more questions, then it's been we can move directly from there. You on the timetable, yeah.
Yeah. Yeah. Yes, I'm here. Okay, guys. So we were supposed today to have this pitch competition, kind of. I don't know if you were able to do that, but the school was very intense. So maybe you didn't have really time to do something, but I want to know from you because I don't know. So if you were able to think about some ideas, if you read the paper, if you had time to think about it, alone, in group, or any kind of mode. Okay, so let's start from another question. Who read the paper? Oh, okay. I'm not surprised that only the women did that. And then it's really, okay, it is a sign of something maybe, right? So I don't know, you would like to, so only the two of you read the paper. So the rest didn't look at that. So the three of you, yeah. Yeah. The rest of the students? No. Okay. Okay. So I will briefly introduce the paper and I will give you, how much time do I have?
Up to an hour, but
Up to an hour.
yeah.
Okay. So you have 20 minutes, 25 minutes to read the paper now. I'm not joking, guys. You can do that. I think in 20 minutes you can read the paper. You don't need to study in detail, but you can have an idea of what is there. So basically, why I give you this kind of homework? Because it's a nice exercise that brings a little bit together what you study in the school, because you saw a lot of open quantum system, dynamics and theoretical framework approaches. So I think, of course, you have only one lecture of quantum machine learning from my eye, so it's not enough to understand, but I think all of you somehow has idea of what does it mean, perform classification, right? Also intuitively. So the idea was to try to combine in one exercise what you learn from the school and what is a practical application of, for example, classification in machine learning. And this paper I found quite easy, so it's quite accessible to everybody, I guess. And basically what it does is creating circuits, very small, in which you have in input basically two density matrix. One is representing your quantum system, and the other one is representing the environment. And they use only 1 qubit to represent your quantum system. And depending on how many input future do you have, so if you have n capital letters input future, then you need here a number of qubits, which is equal to the logarithm of n. And then you have this unitary matrix that basically makes interacting the quantum system described by 1 qubit with the environment. So it's very easy approach. And then how can you use this model to perform classification? You just read out, you just measure only the qubits that represent the system. And then you repeat this multiple times in order to have estimate of, let's say, of the value of these qubits. So what they do in this paper, they compare two different approaches. So one has been described in another paper prior to this, and they propose a new, slightly modification of the method that they propose in the other paper. And the difference between these two methods is how they encode the input, your data that you would like to make sense of. So in the first approach, let's say, they have the system which is represented by equal superposition of a 0 and a 1. So they put an Hadamard gate on that. And the environment is described by n qubits, so the log of n qubits, which also are in equal superposition. And in the unitary that they built, which has this kind of expression, you have a part that describes the quantum system and a part that describes the environment, and the input data are encoded in the diagonal matrix of this unitary, this sigma that describe the unitary evolution, or not unitary evolution, let's say the interaction, the unitary interaction between the quantum system and the environment. So basically your input data are in this tau. And then the parameters of your model are this wi that actually you can optimize. And they compare this method with a slightly different one, in which instead of having your input data in this variable here, in this diagonal, what they do, they decompose this sigma. And okay, this is the learning rule that they use. So the approach, the modification that they propose is that you have this environment, which is described by this out product of the state vector. And in the amplitude of the state vector, you encode your input data. So your input data are x0, x1, x2. They are normalized because you need to normalize when you do amplitude encoding. As we saw in that lecture, you obtain this kind of, now let's say that this, the evolution that, so the unitary that describes the environment, it's slightly simplified because your input data are in the state preparations that represent your environment. And you only have your diagonal matrix that, let's say, you need to maybe optimize the parameter of the matrix. So for the quantum system, nothing changed. You still have. Sorry?
Just F11.
Ah, okay. What is it? No. Oops. Okay.
There you go.
So what I was saying? Okay, so the difference is between only how they encode your input data, and then this imply a modification of the part of your unit that describe the environment. But the one that describes the system still has been defined as the sum of the Pauli matrix. And then what they do, so basically they compare the performance of this method and how they compare, of course, they do a complex state initialization analysis, but how they compare, basically, they do a kind of optimization regarding the sigma q, so how they presented the system, because basically you can weight the sum of this Pauli matrix somehow, so you can find the optimal weight describing this sigma q, or you can also express it in the polar version, so you have a slightly different representation of the same matrix. So, and they compare the method, basically looking at the performance of these two when used for different kind of database. So they try with some real one. So they try the iris data set, wine data set, and this diabetes data set, but also they build up, and these also so 4 real one, but also they build up some artificial database with kind of increased complexity in the structure of the data that they originated. And they basically compare looking at accuracy of the prediction for the evaluating the class of a new data. They look at the F1 score, and also they extrapolate this index, which is it's an index that basically gives you how quantum, how non-classical is your final state, which it's called negativity. And what they end up is that basically they claim that overall, so also they did a comparison of how you encode the data, which kind of normalization you apply. And overall, they find out, let's say, that this new modification of the method that they propose, where the encoding is in the state vector, not in the unitary. So your input data are not in the diagonal elements, but are in the state vector that you use at the beginning. So they find that this kind of method slightly perform better than the other one. So this is a nutshell what they do here. And then what time is it? Let me see. What time is it? 10:30. So you have 15 minutes to read the paper by your own. Yeah, you can do. So, I mean, it's everybody has a laptop or a phone, right? Yeah. Yeah. So you can slightly read the paper in the 15 minutes, and then at 10:45, we can have a discussion, because I think there is no, I mean, I cannot discuss with myself. Yeah, that's, yeah. Okay.
Does anybody know what the Wi-Fi password is? Yes. Yes. Oh, something like that. You go? Oh, there it is. Thank you. Unfortunately, it doesn't show up.
think the time is over. Yeah. Okay. So I don't know how far you could go in the paper, but first I would like to ask if you have any question about that. I don't know how much you were able to read, or maybe from the person that read it all.
And for example, if you have an angel classifier that you are, you've got like, you've got three different types of irises, for example, like a multi-classifier. Why do they, I don't understand why what negativity is and why you.
So negativity is, it's actually, I never saw that definition. I look a little bit, and then here is defined basically as this. Where is it, the definition? So by this quantity here. So basically this norm here of the density, with this partial transpose of the density, basically it's a quantity that what it does, you have your matrix, your density matrix, you swap some row and column. So you re-express the matrix with a different, let's say with this swap, and you look at the eigenvalue of the matrix. If the eigenvalue of the matrix are positive, so this means that it comes from an entanglement state. So you can always, you cannot decompose it as a tensor product. If they are not, then you mean that in principle, maybe you can decompose it in a tensor product of the system. So this, and then it's a measure that says basically how this, after the evolution, so how these entities became less quantum. And then they did this analysis to see if there is a correlation between this quantity, which is called the negativity, that is related to how not quantum anymore is the state, with the accuracy of the models, and they say that basically they are completely uncorrelated. Now, I don't know exactly why they did this, what they want to prove with that, but it's something that I add. Maybe they want to see if accuracy improve if your quantum system stay quantum for longer during the evolution or not, something like this. But I don't know the reason behind this kind of test.
How it makes like 3 class.
3 class. So this is what they do. So basically, in this case, they just look at 1 qubits, and then based on the value of the qubits, if below or above threshold, then and when you repeat your measurement here, you have a certain probability associated to measuring 0 and 1. I think they reduce also the multi-class problem to a binary classification. But in principle, and then it's something, maybe a modification of the model would also be if you describe your quantum system with more than 1 qubits, then in this case, in principle, you can, but you are not forced to measure out, I don't know, 3 qubits, 4 qubits, depending how many do you use to represent your quantum system. And then you can have a multi-classification problem. And this is something that they also propose as future work of these kind of things. Yeah, but I agree, this negativity, I don't know what they want to prove, but what they find is that the negativity, so how not quantum became the state during the evolution, is a completely uncorrelated, it's a random value when they try to find a correlation with accuracy. But I don't know why they did that, what was their goal. This is included. Any other question?
So avete decision area eventually.
Just make sure you're giving them mic, please.
So I'm struggling to make sense on how I would assume that the decision area is where you decide on the results, but then I'm struggling to make sense. For an example, for the A picture, like there's a lot of 0 1s, and for B there's fewer. I don't know how can I decide to make a decision. So basically, I'm struggling to make sense of how to.
Of this figure. So what this is the regional decision of both the two when training on the linear separation dataset defined, okay, using zero linear root, no batches, and training, okay. So they are trying to draw here the decision boundary that you obtain when two, and then basically what they find is depending on how you normalize your input data, if by column or by row, the decision boundary. So when you classify one data to be in one class or the other one, at 0 or at 1, can assume different, can be, for example, for the IQC, you have a completely different decision boundary space. And this just happens when you change the way you normalize your input data. And if you want to use a machine learning model to classify your data, it really matters how you represent your data. And even matter how the normalization is done. So depending on how you present your data, you can have a completely different outcome of your classification. And then it's quite a problem, right? No, because you would like, first of all, a method that is quite, that is able to perform classification in this case for the large amount of data you can have as input. But how do you know how you need to normalize this data if you have to go from one method to the other one? Because if you choose one of the other one, you have completely different landscape. And again, this gets better with the other model that they propose. So this was one strong point in favor of the new way of encoding the input data. Because as you can see, for the method that they propose, this IQC AIL, the decision boundary looks a little bit, let's say consistent, regardless the encoding strategy, the normalization strategy you use.
Also trying to work out how this fits with all the urban function stuff we've heard about.
Yeah.
We looked at like the bar, and we looked at the bar was doing like a series of harmonic oscillators with certain frequencies. So are you encoding the data as those frequencies, or how are you actually, how's the information being put in?
Yeah, it's very straightforward here. It's much easier. So the nice things of this that then all instead of, so in quantum machine learning, you can have a gate-based approach, but also you can have a more, let's say, you can make use of harmonic oscillator in order to make the system evolve. In this case, really, the framework that is used is just based on the fact that you can make interact one qubit with an environment. And the environment here represent all the data coming from the real world. And then they are encoded somehow in your system. How they are coded. So in the first method, in the IQ, the first one, IQC, they encode the data in the diagonal elements of the unitary that they are building up.
Then it wasn't the day, what is that element that we need to change?
What you change is, because each element that is encoded is also parameterized. You have a weight connected to each of the elements of the diagonal. And then basically you can optimize the model, the unitary, the evolution, optimize this W, this parameter.
I think I'm asking, what is the feature of the bath that is being changed, that is being trained?
Yeah. This can be the buff basically is so the buff, the environment, they call it environment. It's represented by this superposition of qubits, right? And then they have this unitary, and this unitary make the system interact with, so one qubits interact with log n qubits through this unitary. Yeah, the system start to, so it's fixed to this superposition, and then it just is this unitary that makes all the work. Yeah, of course, it can be a good point to be explored. I think that one of the goal was now try to challenge it, try to explore, try to modify it. And it would be interesting to have a different kind of unitary that is there, a different way of representing this input data in the first proposal of the model. But do you have some ideas of how
Well, I
to
was just
make...
wondering, can you represent the data as a spectrum and then look at like resonances with the system, or does that?
So what do you mean? You want to extrapolate
So if
frequency of the data, and what do you mean as a spectrum?
Like with the open quantum system. So if you had certain features that reoccur with certain frequencies, then you would have the data would look like some sort of spectral density that you could then use to classify. But maybe it's a silly idea.
Yeah, so basically what they do here is simply you have these weights. I think they initiate the weight to some value, and then each weight is associated to this variable tau, which is a parameter g plus the data, which has been normalized. But you can play with that somehow. Of course, the unitary need to be Hermitian. You need to have some constraint, but I think you can play with that. You can decide what to have there somehow. Yeah, this could be a modification of the of the model.
Yeah, I'll think about it some more.
I mean, in the second approach, I think makes it more intuitive. Maybe it's easier because it's more standard, because you encode your input directly on the state vector, in the amplitude of the state vector and the environment. So make it's more intuitive, and it is more in line with the standard quantum machine learning protocol, let's say.
Thanks.
Maybe, but becomes easier to optimize the model, because then you end up with this sigma environment that has only the weights in the diagonal. So maybe it's easier to optimize that one. So any other ideas, or what you would modify about on this proposed model, or what do you see that cannot really work? Because now something in this paper, for example, they compare the performance of these two quantum models using this database. But what is missing is also a comparison with an approach which use the same kind of formalism, but does not really map this quantum circuit to the open quantum formalism approach. So maybe there is not really robust comparison done with a variational, more classical approach. They didn't explore different way of encoding the data. So what they did, they moved the data from the unitary to the state vector, but they use amplitude encoding. They didn't explore other encoding technique. So this can be another modification. Or for example, when they represented the quantum system, they use only 1 qubits, and the density related to the quantum system is simply the sum of the Pauli matrix. You can make it, for example, more general, use a generic rotation, and then optimize the model on the angle of this generic rotation. Or what else? Yeah.
The fact that when you change the normalization, it affects the outcome.
Yeah, this is what they prove that. But from a classical machine learning perspective, if you have in general, so yeah, you can play, there are a lot of things that you can play with when you perform machine learning. You can play with all the hyperparameters of the model. You can play with how you pre-process the data. You can play how do you normalize the data. You can play how do you represent the data. You can play a lot of things. It's too much. No, you want a model that should be easy going. Let's say you want a model that can be as general as possible. And here you can see that for simple data set, you have to think how to normalize the data. But it's good that they did this analysis. But what they miss here is to explain why, if you normalize in a way or another one, you have a completely different outcome in terms of performance. And then the why, I don't know, do you have some idea why if you change the way you normalize the data, you have a better, No.
Nah, I do not.
What you would
L-
challenge in this kind of model? Do you think it makes sense to represent, to use this kind of formalism in order to perform classification? Does it make sense to you to have this interaction here between a quantum system and environment? What you would change here? It's a simplification of how you can understand the interaction between a quantum system and environment if the environment are the data in the world. And your qubits try to, and then this unitary try to make the system evolve. The system in this case is the interaction between the quantum system and the environment. Do you think it makes sense doing this through this unitary or not? What is missing here? There is something that is missing. I have a feeling that something is missing, but I cannot figure out what. Sorry, that?
On the figure one.
Yeah, on the approach that they propose.
Maybe if they applied maybe gates, quantum gates, maybe if you mean on the circuit.
Sorry, if they apply BB.
Sorry, I mean if they applied more of quantum gates, maybe if you said you don't understand why they do it that way.
No, I don't understand if it makes sense to use this unitary that is making the system interacting with the environment to perform a machine learning task, classification, and in a open quantum system approach. Is this open or not?
Okay.
Yeah, I have the same feeling that there is not too much of open quantum system here. It's just, let's say, the parallelism that they made. So how you do, yeah.
But from the point of view of your reduced system, it's open. Yeah.
Yeah, because you represent data. In the environment, you have some data, you have some numbers that represent the environment. So it's more a conceptual kind of thing. But when you see at the system itself, I don't see a lot of open formalism used. Maybe I'm wrong because I'm not an expert of open quantum system, but you are more than me. But do you mean what I'm arguing here? Yeah.
Okay.
Yeah.
Okay. I just want to understand when they said interactions of open quantum system can improve algorithms and also address the issues of limitation. I just want to understand what they mean.
Yeah, so basically what they claim here that they had this open quantum system formalist approach, theoretical approach, okay? And they compare the classification, the classifier performance on different data set with these two formalism for open quantum system, but also they compare with the result coming from classifier based on a standard variational quantum circuits or kernel method. So I think there are numbers down in the table. And what they find out that this kind of approach outperform over, I think, all the real data set and three, so I think 7, I don't know, outperforming most of the cases the other approaches. They claim this open and the other one are closed, let's say, but I don't see, let's say, what makes this approach open and not similar to the variational approach that they use in the other things. But what they saw that they have some better performance, but still the performance is also based on how they normalize the input data. I don't know. I find it a bit not too open for me. I think it's still a kind of gate-based variational approach to me. but maybe I'm wrong. What do you think? Yeah, with Camille, you
No, so, yeah, I've been in and out, some issue with my stuff. So I missed, I don't know if they explain how they update the weight in the,
so
in the diagonal matrix representing the data, and how they define the cost function.
Yeah, they do a kind of optimization for both, let's say, how they formulated this sigma q, they represent the quantum system. They have different kind of formulation. They introduce some parameters, kind of having a weighted sum of the Pauli matrix. And also what you optimize here are these weight here, and then the rule that they apply for optimizing the weight is a simple learning rule where you have your learning rate. So it's so the optimization is in the parameters, in the weights of the input data in the first case. And the second case, they separate the input data from the parameters. So they just optimize the weight that are represented by the diagonal value of this sigma environment. They do optimization.
Okay, and how do they define the cost function?
The cost function is simply given by where is it? I think they use a classical optimizer. I think like I didn't, maybe Adam optimizer.
Because depending on the kind of data, I guess they change the cost function.
No, the cost function is so the goal is to obtain this classification. So the goal is they trace out an environment, and they want to find basically the probability of finding a 0, finding a 1. And so basically the cost function try to maximize the probability of finding the right class. And in all the cases that they have supervised learning settings, so they know what they are looking for, so they can simply define a simple cost function and comparing the probability distribution that they obtain for the 0 and the 1 with the expected one.
In the sorry.
Thank you.
I think we spoke a little bit about what was missing. I have a small idea.
Yeah.
Did they forget the adjoint of the unitary?
The adjoint of the unitary, they forgot to, why? No, I think they use it here when they calculated when they performed the measurement. What do you mean where they forgot the adjoint? Because they're not calculating a kernel. So it's they're just encoding the data, and I think, in the measurement part they make use only.
I was just asking because when it comes to working with stuff like this, we need like probability to be conserved in this case. So that's why I was asking, if we use the unitary operation, then we'd have to put the adjoint somewhere in order to have that conservatism of the probability. But yeah.
No, what? No.
Yeah, I guess it's a little bit misleading the diagram because in like based model where you're in pure states.
Yeah.
If you take a pure state and map it to a pure state, it's just a unitary.
Right.
But as you said, if you're dealing with density matrices, it's like U row, U dagger.
Yeah.
Basically, that's what the diagram means. But they just represent it in
a bit density.
Right. Okay. Okay. Thank you.
So what do you think, to conclude? So what would you do if you would like to perform machine learning using quantum computer, but using an open formalism? No idea. No idea.
This is a very broad question, but is there any kind of indication of any advantage?
They say that it is better. They say that it's advantage. Yeah, there are some papers where they claim using very different way. So for example, they claim it, but they have to change the normalization of the data. Something that you say, okay, actually you always normalize using the normalization. So it's, I don't know. Some papers they claim that is their advantage, but the streets that they decide to undergo to claim the advantage, it's very bumping because sometimes they have to do something that's quite exotic. For example, change the normalization that it's a bit exotic to do. But in principle, yeah, they say that you can have an advantage here, and one of the problems is also how do you benchmark these kind of things. What they did, they compared to quantum formalism and they compare to other quantum formalism. They find that in some case they perform better, in some case they perform worse, but it depends on the data that you use, how you encode your data, and how you make it. Yeah, of course. So there is not a clear idea, but in some specific case they say, okay, it's better from some specific case. Yeah.
So this is maybe a very stupid question. If we're talking about changing the normalization, I would have thought the normalization would be fixed, because if you're encoding, doing an amplitude encoding, then the normalization is just your states have norm one.
Yep.
So why it's not a variable?
No.
Favorite.
No, but apparently it has an effect. Apparently it has an effect. Then so what they don't explain is why. And I was wondering if you have some ideas why. Yeah, apparently it does. They change the performance of the model. So I don't know if you have some final remarks on this. I don't know how much time do I have, but I think it's better when you try to understand something, you see how you have to do that. What does it mean? And I think there are a lot of attempts in doing something in quantum machine learning that come from more a theoretical approach, for example, open quantum system. I don't know if you saw a little bit of the introduction. There have been different kind of way and approach of doing that. But it's very difficult when you try to apply this for some specific problem to prove that they are good or not. And also there are a lot of open questions that are not answered. For example, they didn't answer, okay, from where this better performance is coming from, why for certain data is performing better. They say that maybe actually they show that for the iris dataset, that was one of the simple one, they have better performance, and they explain that saying, okay, because iris is a simple one, okay. But in other, for example, in the variational quantum circuits, what has been proved is that you have a better performance when you use data that have a complex structure in it. So the quantum computers make it, the quantum machine learning give better result than, for example, classical counterpart, based on the results that you obtain applying it to some random data set. So, but there is not yet a clear idea of why to perform in this way. And in particular, I want to talk about this because this open, let's say, formalism that they use, to me, does not really make too much sense. But I don't know how to make it more open than it is. Or if it's already a variational quantum classifier, it can be considered as an open quantum system interacting with the data representing the environment. So this is what they did here. Yeah. So that's all. I don't know if you have any other final remarks or final question or ideas. If you have, just speak now. No. Okay. Okay, then we are done. Thank you.
I think we have like let's say 15-minute break, and then we'll try to get the last two talks in the remaining hour, and then 12:30.
One. One.
Yeah, so just to recap what I talked about yesterday. So in yesterday's lecture, I introduced ways of how we can formally characterize non-Markovian quantum processes. So I mentioned that for classical stochastic processes, we have a way of well, Markovianity has a formal definition in terms of the conditional probability distribution. Generally, we can't extend this classical definition of Markovianity to the quantum domain due to the fact that we generally can't construct endpoint probability distributions that satisfy the what's called the Kolmogorov consistency requirements. And this is due to the fact that, in quantum mechanics, measurement has a non-trivial role, whereas in classical mechanics, we can measurements don't have a kind of inherently disturbing effect on the system. So due to that, there's been a lot of ways that people have tried to characterize non-Markovianity at a quantum level. These kind of are roughly can be roughly categorized as either global definitions or kind of reduced definitions. So there's a whole zoology of kind of concepts that are related to each other in this diagram. So yesterday we looked at kind of some characterizations of non-Markovianity that are based on a kind of reduced intrinsic picture. So that these are definitions which are intricately linked to the so-called quantum dynamical map. So it's basically a map that tells you how your system evolves under the interaction of some environment. So the two, like, you can maybe not read it properly, but the highlighted version on this kind of diagram is the concepts of so-called divisibility and distinguishability. So just to kind of very briefly recap, divisibility. So generally, due to the fact that we can, under the requirement that we have factorizing initial state of the system environment, we can construct a completely positive trace preserving map that describes the evolution of our system. Generally, the mathematical inverse of this map at least exists. That allows us to kind of define a two-parameter family of maps that here I call lambda, such that the time evolution, if we take a system and prepare it in some state and evolve it over some time interval, this is equivalent to taking our state, evolving up to some intermediate time s, and then evolving it up to some later time t. Generally speaking, even though this map phi, you can see my cursor, yeah, this map phi of t is by construction completely positive and trace preserving, there's no such requirements on this intermediate map. So this intermediate map can be non-CP, non-completely positive, or not even necessarily positive. And so P, there's these two different characterizations where we say if this map is positive, then the process is P divisible. If it's completely positive, it's CP divisible. And we say that generally a non-Markovian, according to this divisibility notion, a quantum process is non-Markovian if this intermediate map is CP indivisible for all choices of S, basically. Okay, and so the Markov semigroup I mentioned is according to this definition, is by construction CP divisible, and so therefore Markovian, as we would kind of expect. I won't go over this bit too much. So, so ways that we can kind of based on this notion of divisibility, we can construct a kind of measure that we can compute that can tell us if we have a quantum process that is non-Markovian. So this is done using the so-called Troy matrix. Again, I won't go over the definitions, but essentially one can show that if this intermediate map is completely positive, then this implies that the corresponding Troy matrix is a positive matrix. Similarly, if the intermediate map is completely positive, then this implies that the trace norm of the Troy matrix is 1. If it's not completely positive, then it's greater than 1. And so this, actually, sorry, this formula is slightly wrong. It should be this trace norm -1 divided by epsilon. So there should be a -1 in the numerator. So essentially, this definition of this measure, using these properties, implies that if we have a CP divisible process, then this measure is 0. So it's Markovian. If it's greater than 0, then it's not Markovian. Okay, so we also talked about this, the notion of distinguishability. So this has some kind of notion that's rooted in quantum information. So basically, the trace distance tells us the distinguishability of any two quantum states under kind of one-point measurement protocol. And it obeys this kind of monotonicity behavior under completely positive and trace preserving maps. So in other words, like if we have two quantum states, rho and sigma, if we evolve these under some kind of any completely positive trace preserving map, then this will always decrease the trace distance. And this kind of has some interpretation in like a loss of information that, if we generate one of two states and we're able to distinguish these with 100% probability at some initial time, if we evolve these states under a noisy channel, representing the interaction environment, generally the likelihood that we're able to tell which state that we were originally given with a measurement generally decreases. So that's kind of what's schematically represented here. And so this allows us to kind of build a definition of non-Markovianity that's based on this idea of information flow. So we can say that according to this, the trace distance, the quantum process is non-Markovian if for some pair of initial states, the trace distance obeys a kind of non-monotonic behavior. So schematically, that's what's represented here. So based on the monotonicity property of the trace distance, it always has to decrease from some initial value. So if at t0, for example, the trace distance is 1, if we evolve some pair of states over some time interval, the trace distance always has to decrease. But according to this monotonicity property, but it doesn't tell us anything about how the trace distance has to behave as it decreases. So there's kind of qualitatively two different behaviors. One where the trace distance decreases monotonically, represented by the blue line, and one where it decreases non-monotonically. So non-Markovian processes are those in which the trace distance decays non-monotonically. And the blue one, the monotonic case is for Markovian process, and that Markovian processes. And I mentioned that this is kind of connected to this idea of information flows. So this kind of trace distance between these two states represents the kind of amount of information. And so in the case where you have a Markovian evolution, when the trace distance decreases, this represents a kind of a loss of information from our system to the environment. And this just happens monotonically. So this information is just continuously lost from the system into the environment. Whereas in non-Markovian cases where you have this non-monotonic behavior, what happens is that whilst information is generally lost, you can have the kind of time periods where there's a kind of reversal of information flow. So information can kind of come back into the system. So this kind of presents a quite nice kind of information-based picture of quantum non-Markovianity. Okay, and so a kind of important, I won't go over kind of the details of like proof, but these two kind of concepts are related to each other. So the divisibility and distinguishability criteria. So what one can show is that any quantum process which is divisible is automatically Markovian according to the distinguishability criteria, in that it always produces a decreasing state distinguishability. But the converse statement is not true. So if you have a decreasing state distinguishability, it doesn't mean that your process is divisible. So there are some specific models where there is a kind of a bilinear relation where these two things give exactly the same criteria, but generally there's this kind of symmetric relationship between these two concepts. Okay, so I thought I'll just apply it to like a very simple example. So the example that Marco introduced in his lectures was this a case where you have a two-level atom that's placed into a reservoir, so a vacuum reservoir. So the total Hamiltonian of this model is given as follows. So you have your local system Hamiltonian. So you have essentially a system that has two energy levels, that has an energy splitting omega naught. So because I'm a theorist, H bar is always 1. So there should technically be H bars here, but they're just 1. You have a reservoir which is made up essentially of a very large collection of bosons or photons. And then you have this kind of special number conserving interaction between the system and the reservoir. So as kind of Marco mentioned in his talks, because you have this number conserving property, this model is actually exactly solvable, which is generally not true in open systems theory. Again, I won't go over the details here because I don't have enough time, but I encourage you to consult Marco's lecture notes to see the exact solution. So I should mention here, this should not be one of these G's should not be a complex conjugate. So there's a little bit of a mistake there. But what also Marco, so because this model is exactly solvable, what we can do is also write down a time local master equation that describes the dynamics of our system in terms of these kind of time dependent quantities that we call S and gamma. So this S and gamma can be extracted from these coefficients. So here, if you recall from Marco's lecture, the CE is kind of like the excited state amplitude of our two-level system. So the mod squared of this quantity gives us the probability of our system being an excited state at some time. And so because this model is exactly solvable, we can extract, for a particular type of spectral density, we can solve for the C of E exactly. And so these coefficients are defined in this way. So sometimes, this is given a label S because sometimes people refer to this quantity as the so-called Lambert shift. So it basically describes how the system energies are renormalized due to the coupling to the environment, and this gamma is kind of interpreted as a decay rate, although kind of time-dependent decay rate. Okay, so as you might recall in the last lecture, I mentioned that you have to be very careful when you're dealing with time local master equations. Time locality doesn't imply Markovianity, and this is in fact an example where, based on the behavior of this decay rate, you can get non-Markovian behavior. We can just so with this kind of master equation, what we can do is apply this, for the just looking at the divisibility, the divisibility criterion. What we can do is apply this, or we can compute this quantity that we call G that acts as a measure of the non-Markovianity. Again, there's a mistake here. There should be a -1 in the numerator. Essentially, okay, I haven't. I'm not sure if I should write it down the board, but basically, this L of t is basically the generator of the dynamic. So basically, this super operator L of t is the right hand side of this equation. Okay, and so to compute this quantity G, what we do is we take this super operator and we tensor it with an identity that it belongs in a two-dimensional Hilbert space, and then we apply this to the maximally entangled state of our system. So in this case, we're dealing with a two-level system. So to compute the Troy matrix, we have to dilate this super operator onto a two-dimensional, or using a two-dimensional ancilla. So we're working in effectively a four-dimensional space. So I'm skipping a few technical details here, but the way that you can do this is by using this property, which is known as vectorization, which essentially there's this kind of isomorphism between super operators and matrices on kind of doubled Hilbert spaces. But again, I won't go into this. So basically, but essentially what you can do is you can construct this quantity here as a 4x4 matrix. You can compute its trace norm exactly, and then you can come up with effectively an expression for this G. And if you do that, again, there's quite a few technical details that I'm skipping here. But if you do that, you can basically show for this model is that this G is identically 0 if the decay rate is positive. Whereas in the case where this is negative, it's proportional to the minus gamma of t. So if you recall, the definition of this measure was such that if it's 0, then your system undergoes a Markovian process. If it's greater than 0, then the process is non-Markovian. So what this result implies is that for this particular model, the dynamics is non-Markovian if the decay rate becomes negative. So I haven't applied the exact example or done the exact example here for the case of using the distinguishability criterion, but you can in fact show, actually it might be a nice exercise, but you can in fact show that for this model, the trace distance predicts qualitatively the same criteria for when the dynamics becomes non-Markovian. So namely that the decay rate becomes negative. So for this particular model, divisibility implies distinguishability and also the converse as well. And so this is just an example. This figure here is just an example of a case, or it just plots this decay rate t as a function of time. I mean, maybe it's a little bit hard to see, but this shows an example where for certain sets of, so for a particular type of spectral density, if the system interacts strongly with the reservoir, then you get this kind of behavior in the time-dependent decay rate where for certain times you can see it. So this is just 0 here. You can see that for certain times the decay rate goes below the 0 value. So this is a part where it becomes negative. So you can see this is an example of kind of non-Markovian behavior. And so actually, again, I don't have the details on this slide, but if you this has a kind of quite nice interpretation in the case where you look at the trace distance quantity in characterizing the non-Markovian behavior, because the interpretation is that at times where this decay rate is negative,
information can kind of return back to the negativity of this decay rate indicates a kind of reversal of information flow from the system to the from the environment back to the system. And so there's again, this is maybe a bit superfluous detail, but there's another formalism in open systems that's called this non-Markovian quantum jumps formalism. And again, this kind of negativity of the decay rate has this nice interpretation whereby what happens is that if you start in a superposition state, the interaction with the environment generally corrupts the information that's contained in the superposition state. But when this decay rate becomes negative, you can kind of have reverse jumps where information that's lost to the environment can kind of come back to the system, and your system revives some kind of coherence that it previously lost. So, you know, some of you who have like a kind of quantum information background know that decoherence is generally bad for building quantum computers for precisely the reason that if you prepare something in a superposition state, it generally loses that coherence with time. But this is an example where, you know, you can kind of get revivals of that coherence due to the fact that you have this non-Markovian behavior. So, you know, non-Markovianity is quite interesting from a quantum information perspective. Okay, so I'm not sure how much time have I got left, like just over 10 minutes. So, okay, I'll jump very quickly because I was also mentioned that I wanted to introduce this framework, which is called collision model. So this is something that's slightly different, but I think maybe is hopefully of interest to some people. So far, when we talked about open quantum systems, we have this visual picture of a quantum system that interacts with an environment, and this environment is continuous in the sense of it's made up of a very, very large number of degrees of freedom. So that's kind of one very, very well used model in open quantum systems theory, but there's this kind of another kind of framework that people use to analyze open systems, which is called collision models. So this is a kind of a slightly separate framework whereby instead of the environment kind of being continuous, you assume the environment is made up of a lot of discrete kind of ancillas or particles. And so this is kind of what's diagrammatically represented here. So you have your open system S, and then your environment is kind of, as I said, a kind of composite of lots of these small ancillas or particles. Okay, and then what happens is that, so what's kind of implicit in the name collision model is that the way that you model the interaction between your system and environment is that your system kind of collides with each of these particles in sequence. So that's this kind of little animation that's meant to be showing this here. I don't know if you can see it. Like, so your system starts in some state, it collides with ancilla A1. Okay, it's a little bit quick, but then it collides with ancilla A2, etc. So it just kind of, each of these interactions is described by a unitary operator. So you have a kind of interaction, the system moves on to the next ancilla, etc., 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 and you just continue indefinitely. And so the way that you can describe the dynamics in this type of model is, you know, through a kind of standard open systems framework. So what you ideally want to do is to come up with an equation for the density matrix of the system alone. And so to do this, you can, we just note that states on this kind of, in this picture are basically described as basically, so if you, for example, if your environment is made up of n ancillas, states of the system plus environment will basically be of this kind of have this tensor product structure. Okay, so the reason that collision models are interesting is because they kind of provide some kind of, they're relatively simple. So, you know, you just have at any two instance, you have a system that collides with an ancilla, and then, you know, just repeating this process over and over. So, you know, the system and each of these ancillas are usually very basic. So, you know, they could just be two-level systems or a two-level system and a harmonic oscillator or something like that. So they're quite interesting because they generally give you quite a high degree of control and flexibility over the types of dynamics that you want to describe. So they're quite an interesting kind of lab for looking at things like non-Markovianity and in open quantum systems. So in the very basic model, you assume that your system is uncorrelated with the environment, as you usually always do in open systems theory, but you also generally, just in the simplest case, assume that each of these ancillas are kind of uncorrelated with each other. So the initial state can be written in this tensor product form. And then, as I said, the system collides with each ancilla up to the nth ancilla via a unit tree. So generally, you also assume that this unit tree at each, I mean, in principle, it can be different, but generally you assume that this unit tree is just the same at each step. And so to then generate the dynamics, you just say after n collisions, the state of your system plus the environment will be the state of your system plus n ancillas. So this U here is like a kind of super operator that basically just applies like a U1 dagger to whatever state it's acting on. So it kind of, the general structure of your state looks like this. So in the basic models, we also assume that collisions only happen with the system and each ancilla, so there's no kind of internal collisions. Okay, so in the case where, you know, that if each of these unit trees are the same, and you also assume that each ancilla is initialized in the same state that here we call sigma, and we assume that all these ancillas are uncorrelated, then the state of your system plus environment after n collisions looks like this. What you can then do is, you know, as you always do in open systems theory, is you trace out your ancillas if you just want to, or you trace out the environment. If you just want to look at your open system, you just trace out the environment. In this case, you're basically tracing over every ancilla. And so what you can do is, so if you apply this trace, what you can note is that at each step, the system only collides with one ancilla. So A1, A2, A3, etc. So what that allows you to do is kind of pull in the partial trace into this expression up here. So obviously, you know, here at the first step, U is an operation on SA1. So therefore, we can pull the trace over A1 into here. At the next step, this U operator is an operation on SA2. So again, that allows you to pull the trace in. So that allows you to come up effectively with a quite neat, compact expression for the reduced density operator rho S in terms of this, you know, infamous object that we always talk about, the dynamical map, which is, as I said, it's just basically a map that takes states of your system onto itself. And so in this sense, what you can do is define a map in the following way, where here this A is just any ancilla, so it can be ancilla A1, ancilla A2, ancilla A3, etc. And you know, as I've talked about extensively, and as also Marco proved in his lectures, is that any map that can be written in this kind of form, so where you have a tensor, you have a system that's tensored with an environment, you apply this kind of U dagger operation, and you take the trace. This by construction is completely positive and trace preserving, so it has nice properties that we want. Okay, and so if we just apply this definition of this map to this expression, you can show that in this kind of basic model, effectively what your dynamics is just the repeated application of this map n times. So that's what's kind of represented here. So this phi to the power of n basically just means we apply phi to the initial state of the system, and then we compose this with the same map, compose it with the same map n times. And so kind of diagrammatically, what this represents is the following kind of operation. So at the first step, so if we just take n is equal to 1, that just describes the first collision. So the collision of S with A1. So we take S, we apply U to both S and A1, and then, so let me just go back to this slide. So here, this map describes like the U operation here, and then what we do is after every application of phi, we take the trace. So that's kind of what's represented here. So we take S, we collide it with A1 via U, and then we take the trace over A1. So kind of what this trace operation here is doing is deleting the ancilla from the picture. And then we continue. So for n is equal to 2, we take S, interact with A2, apply the trace, and then we you know, this is equivalent to deleting A2, and you keep going. And so you can see that this kind of intuitively describes a purely Markovian dynamics in the following sense. So because the system, because each ancilla is prepared in the same state, and because S collides with each ancilla via the same interaction U, you can effectively see this picture, or you can map this kind of picture of the dynamics to a simplified one where S basically collides with the same ancilla at every step. And that's kind of, this detail is hidden in this kind of structure up here. So at some kind of, let's say the system has undergone n collisions. At the next step, so the n+1 step, what happens is our system will be, and the next ancilla, so the n+1 ancilla will initially be in this state, right? Because, as I said, each ancilla in the environment is initially uncorrelated with the system. So obviously they're going to start uncorrelated if they haven't interacted yet. And then what happens is that as what's, you know, as to then get the reduced state of our system at the n+1 collision, we apply this map phi, which is just U dagger applied to this state. So what happens is that as when S and A interact, they basically become kind of correlated. So A picks up some kind of information about the system, and then what we do is we apply the trace, so as represented up here. And then effectively what that does in this kind of simplified picture is you're effectively deleting all information contained in A about the system, so in correlations and also in the state of A. So this is this kind of ancilla reset operation that happens where after S and A collide, you basically delete all correlations and information in A, and then a fresh ancilla, A is effectively refreshed into the same state that it started in. And then to go to the next step, you just repeat the same operation. So intuitively, you can see how this describes a Markovian dynamics because there's no memory. The environment holds no memory of what it did, you know, how it interacted with the system. So the system, at any given step, the system collides with this ancilla. There's some kind of information transfer, but then we basically delete all this information and throw it away. And so the next ancilla that comes along obviously knows nothing about what's happened previously. So again, this is kind of intuitively how you can see Markovianity. And also, just from like, you know, formally, just from the definition of Markovianity that I gave, this divisibility criterion, you know, by construction, because the map that describes the evolution of our system after the n collision is given by the nth power, this map is inherently divisible. Because obviously, you know, phi to the n can just be written as phi to the n minus m times by phi to the m, where m is just any number between, you know, 0 and n. So just formally, according to this divisibility criteria, this dynamics is Markovian, as we would expect. And okay, this is just essentially the Troy matrix that I gave previously. Okay, I think I'm probably almost out of time. So, but this is just to kind of highlight. So this kind of basic collision model framework where you have a system that collides repeatedly with ancillas that are initially uncorrelated can only describe a Markovian dynamics based on what I just said. But you can kind of have interesting generalizations of these collision models to non-Markovian cases. And the easiest way of doing this is to consider cases where you don't just have collisions between S and A1 at every, or S and A2, you also have collisions between ancillas. So S will initially collide with A1, but then before S collides with A2, A1 collides with A2. And then, you know, S moves on, collides with A2, and then A2 collides with A3, etc. And so intuitively, you can see how this might describe non-Markovian dynamics, because this kind of extra collision that you're adding between each of the ancillas kind of allows you to pass information through the environment about the system. And so therefore, at later, you know, if S collides with A1 and A1 collides with A2, when S collides with A2 in the next iteration, information can kind of come back to the system. And so this kind of describes you know, intuitively some kind of, intuitively there's some kind of memory that's being held by the environment in this step. Similarly, you can initially correlate your ancillas. And again, this has the similar mechanism where information will be stored in the environment about the system that can kind of then return to the system. Okay, So I think I'm probably out of time now. So I don't think I had many more slides. Yeah, but okay. Let me just stop and yeah, say if you have any questions. Yes, I don't know if you have a mic there.
So more a comment than a question, but this reminds me, at least the Markovian version reminds me of a model of micromaser action. Micromaser being a system where, for example, model two-level atoms go through a cavity and interact with the cavity field and then leave the cavity. So it's a beam situation. And you can have a repeated sequence of atoms going in, interacting, going out, and then the next one goes in, interacts, and goes out. And I think this also has a master equation. It probably corresponds to the Markovian collision case.
For these, I haven't gone over it here, but for these models, naturally it describes a discrete time evolution, right? So you have one collision, two collision, three collisions, etc. But what you can do is formulate a kind of continuous time limit, whereby you say that, because here there's no notion of time, right? Like n is just a natural number, but what you can do is say, you know, S and A1 collide over some time interval that we call delta t or something. And then we can define a time interval, which is t is equal to n times delta t. So, you know, basically that's saying that the system over a fixed time interval, the system will undergo n collisions with the environment over a fixed time interval. And then what you can do is take the limit that dt goes to 0, which is the kind of continuous time limit. And you can show that in those cases that you can write down a master equation for your system, which is a Markovian master equation. So so I think those models you're talking about are where you can write down this master equation is basically the continuous time limit of what's given here.
So there's a time limit taken.
Yeah.
I don't remember the time limit, but then it's a long time since I saw the model. I mean, the model certainly starts with a finite time interaction and then, you know, builds up time from having a sequence of these atoms going through the cavity. And then, of course, the interest is in what is the field inside the cavity doing.
Yeah.
But in the micromaser case, I think in that master equation, probably what you call ancilla atom here is discarded. But equally, you could do a measurement on the ancilla. How does that affect things, do you think?
So you mean the system collides with an ancilla and then you perform a measurement?
Measure it, and then, of course, you know, the way you treat what's happened is no longer, you know, being dealt with by the trace operation, but by projection on the ancilla part. Has anyone looked into that? Does that lead to a Markovian master equation, or I don't have an idea.
I would assume that if you don't have any collisions between ancillas, so if you just have this same basic model, but you measure the A1 after each step, I don't think it would change the structure of the model in a sense, because what you're doing is, what it would do is just change the definition of this map phi, because what you would have is kind of rho S tensored with this, you have your collision that's described by this U, and then you would have another super operator kind of embedded in this map, which describes the let's say a projection on the ancilla. And I think that, if I'm not mistaken, this would still have the same kind of structure, or actually
so the projections would be non-unitary,
yeah,
and the results of the measurements would be a bit random depending on.
Okay, maybe you can't hide the measurement in here, but I think what you could maybe do is you would have this, you know, collision U, and then you would compose this with a projection on. Okay, I'd have to think about it a bit more, but I think that you could.
It's just a thought. No.
Yeah. My intuition would be that it. Actually, potentially it could affect because if you measured A1, you're generally, well, okay, we can talk about it afterwards, but anyway, yeah. Okay, since I'm over time, then I think I can just move on to the next. Oh, yeah, sorry.
Just one quick question. On the first part with the negative rates, you mentioned this is only for this particular model, but is it possible to make a more general statement about negative rates, master equations, and non-Markovianity?
Yeah, so not in this lecture, but in the previous lecture, I came up with this. So you can show that generally speaking, you can, if the map inverse of this map exists, you can always write down a master equation which is in this form. Okay, generally, you can prove the existence of this master equation, but you don't actually, to actually calculate these things, generally it's difficult. But for this divisibility criterion, you can show that, you know, in the case where all these are positive, then it will be CP divisible. You can also formulate P divisibility, which is a slightly weaker condition, which is this one. So you can generally, as long as you have a master equation that has this structure, then yeah, you can come up with, which is essentially what I showed in the example, because in that example, you only have one decay channel, so one decay rate. And when that becomes negative, that was Markovian according to this G quantity that I introduced. And so that's just consistent with this. So that's when basically when G becomes negative, this intermediate map becomes CP or loses its complete positivity. Yeah, so. Yeah.
Can I just make a comment on that?
Yeah.
When, as you probably know, when those rates go negative, that's exactly when energy or information is returning from the pseudomode to the original atom, and it matches that exactly.
Yes. Yeah. Okay, we can, I think, move on to the next paper. So.
Yeah, 100%. Yep. Okay, there we go. Okay, so today I'm going to give you a very brief overview of quantum mechanics in biological systems in a broader sense. So in the last two lectures, we focused on photosynthesis and specifically on the theoretical description of rates and so on. So in the first part of this lecture, we are still going to focus on photosynthesis, but this will be conceptual. So you remember our Fenner-Matthews-Olsen complex that acts as a wire to transfer energy from the fluorosome, which harvests the sunlight. It has these 7 pigment molecules. And then in the last lecture, we spoke about nonlinear or spectroscopy. We said that the nth order polarization has to do with n interactions with the electric field. So we have n light pulses, and then we look at the signal. In general, the signal can be deduced from this response function. In the linear case, the response function has this form. And we said that
this is the expression for the absorption spectrum. It's the Fourier transform basically of the response function. So for more details about spectroscopy, there's a mini school that we did last year, but contains most of the information in my last talk, and it's also focused on spectroscopy. Just briefly, we considered first order spectroscopy, that was just absorption, but spectroscopic technique that is often used is third order spectroscopies, specifically 2D electronic spectroscopies. 2D electronic spectroscopy is somewhat confusingly a third order linear spectroscopic technique. And how this works is we illuminate the sample with 3 light pulses. There you see the 3 light pulses coming from the directions, or traveling in the directions as indicated by the red lines there. And the signal is then detected in another direction. So we have 3 interactions of the pulses. Third order technique, we see the signal. And the way we detect the signal is just by putting a 4th pulse there, but that's simply for detection purposes. It's called heterodyne detection. So we have control over these time periods, the tau, capital T and small t. And we can control them by placing glass wedges in the setup to slow down the light. So we see the signal as a function of these 3 time periods. So we have a 3-dimensional, or we have a block of signals, a block of intensity values. We can then Fourier transform over these 2 axes, the tau and the t axis, so the first time period and the third time period, to get the block of data in this form. This, one can think of this as the frequency at which we excite the system, the frequency at which the system de-excites or emits, and such a 2-dimensional spectrum we get as a function of the so-called population time, the third axis. We can directly probe coherences between different exciton states. So we can look at how the different eigenstates of the system Hamiltonian superimpose and the superposition of those states by probing these off-diagonal elements. And if you do that, you see, which you also showed in saw in Neill's talk, you see these oscillations, which are signals for interexcitonic coherences. And this caused quite a stir in the community. This would imply, because these coherences are on the same order as energy transfer, the same time order as energy transfer. So perhaps these coherences could be important for energy transfer then, or some people even suggested that plants may perform quantum computations. But in calculations, such as this one, the coherence is not seen to last as long as in some experiments. So the coherences in the experiments last for longer than what is expected from simulations. Here I show just the FMO complex, and the exciton states more or less are drawn by those lines around the different pigment molecules. So you can see that each exciton is comprised of either 2 or 3, generally speaking, pigment molecules. And we can calculate the population of these exciton states as a function of time using something like the rate field theory, in some master equation. And you see that how the populations change, but you see that the red exciton, which is this exciton, gets excited most at thermal equilibrium, or eventually, and that is exactly what you want, because you want to transfer excitation from the top there, from the base plate, through this FMO complex to the reaction center where the chemical reactions that produce energy-rich compounds are started. There were some questions about whether quantum mechanics is necessary at all to describe this flow of energy. So in this article, you can see how the classical calculation of the populations of these exciton states correspond to the quantum calculation. So it's clear that describing this process classically is not sufficient. You just get that all the excitons have the same final population, and that would not form a very good energy conduit. This figure is from the same paper, Charles et al. And it shows the pigment molecules. It's a bit unclear, but the greener something is, the more excited it is. And actually, you can't see it on the projector, but there's also these thin outlines that show the exciton states. And this is just to show in time how excitation flows through the FMO complex. It starts off at the top and eventually it ends in the bottom. So the current view is that coherence itself, the superposition between excitons, is likely not important for photosynthesis. But in photosynthesis, the interaction between the pigments and the coupling to the bath is fine-tuned. It means that that photosynthesis doesn't use quantum mechanics in this sense that we like to think of it with all the strange quantum effects, but it uses quantum mechanics in the sense of an open quantum system and tunes the parameters so that excitation transfer is optimized. One can think of this, or some analogy that's sometimes used is playing soccer or football. The size of the ball has to be just right. If you play with a marble, the ball will get stuck in the little divots in the grass. So then the excitation would go nowhere, it would just be localized on a pigment molecule, and excitation would not flow through the system. If you play with too big a ball, then the excitation is everywhere and you can't score a goal because the ball is just the size of the pitch, of the field. So the excitation has to be right size, and that is fine-tuned by how these pigment molecules interact among themselves to form the exciton states, and also how they interact with the bath. So what causes the oscillations in the nonlinear signals? I won't go into this in detail, but it has to do with vibrations, or it's accepted generally, I think, that it has to do with vibrations in the pigment molecules, and the dephasing of coherence in these models are slow because the same vibration, or because two vibrational levels on the same pigment are involved in the superposition and therefore coupled to the same bath. So it's not really electronic coherence. It's not that these exciton states are in a superposition. It's rather that the superpositions you see in the spectroscopic signals are superpositions between vibrational levels, involving vibrational levels that are coupled to the same bath, and therefore dephasing is slower. To learn more about photosynthesis and the quantum mechanics involved in photosynthesis, you can use these 4 books. Now, let's look at quantum mechanics in biological systems in a broader sense. We'll look first at how birds may know where to go, how we may smell, how our enzymes may keep us alive, how we may think, or maybe not, because none of these hypotheses has been conclusively shown. So, yeah, but we also have to keep in account that quantum mechanics exists everywhere. Quantum mechanics is in chemistry is basically quantum mechanics. So it's not always obvious where to draw the line when you speak about quantum effects in biology, because everything necessarily involves quantum effects. But let's go to birds. This is a map of the migration pattern of barn swallows. We also see them in South Africa. But how do these swallows know where to go? Why don't they fly off to Brazil? They did some experiments. They placed birds in a funnel such as this, and there was an ink pad on the bottom, and the funnel was close to the top. The bird sits on the ink pad, and then when it takes flight, you get out of the funnel. During migration season, it would jump off into the direction of migration. That was the hypothesis. But when they place these birds in wooden huts, they didn't see any preference for direction. So there was no, the birds didn't seem to have a sense of direction. This was strange. So they basically put Faraday cages inside the huts, and they did the experiment again, and then there was strong preference for direction. So the conclusion that they made is that the birds were influenced by electromagnetic noise, because this was done in an urban setting, or in close to a city. And they could induce the same poor sense of direction when they created artificially electromagnetic noise. So they showed in this experiment that birds somehow use magnetic sensors to navigate. How can this work? What could be the mechanism possibly for such a biological compass? Already in 1978, a mechanism based on quantum mechanics was proposed by Klaus Schulten. And he proposed that the singlet, that there might be some biological complex that could be in a singlet or a triplet state. Singlet is just the electrons in an opposite configuration directions, and the triplet state is when the electrons are point in the same direction. Perhaps the Hamiltonian that describes the dynamics of such a system, which can both be in a singlet and a triplet state, could be influenced by the magnetic field. For instance, through the Zeeman interaction. You've heard a lot about that. The Zeeman interaction, which splits the energy levels of opposite spin systems. They knew about this protein called cryptochrome 4, and they knew that it could form radical states. So when it is excited by blue light, the donor donates an electron to the acceptor, but you get the product in both the singlet and the triplet form. They investigated this cryptochrome 4 protein for migratory birds like the swallow, and also for birds that don't migrate like chickens. And they saw that the cryptochrome 4 from migratory birds were indeed more sensitive to magnetic fields. So perhaps cryptochrome 4 is involved with navigation. Cryptochrome 4 is found in the eye of birds. And as I said, this molecule can become excited by blue light to form this product, which can donate an electron from one side to the other to create a singlet and a triplet state. Both of these can form a certain product. I won't go into detail. But the singlet state can also be transferred back to the ground state. So you could think that if you were only in a singlet state, then you would have less product because some of the singlet would be transferred back to the ground state. So the amount of product could be influenced by the ratio of singlets to triplets, and that in turn can be influenced by perturbations on the Hamiltonian. And the mechanism, one proposed mechanism, is that this product interacts with the with the eye of the bird. So perhaps when birds fly along the magnetic field lines, they see an effect. For instance, they may see a bright blob where these products are formed. Yeah, but when they turn away from the magnetic field, this product is formed, perhaps so this bright spot might decrease in intensity, something like that. We can't ask birds, so for the moment we don't know. Okay. Another thing where quantum mechanics may be involved is our sense of smell, olfaction. So we have these olfactory nerves that let you smell stuff. Technically, it's called the G protein coupled receptor, but the one hypothesis of how this worked, for long they accepted hypothesis, was a so-called lock and key model. So whatever you smell, let's say this was some perfume molecule or something that you can smell, would fit into the receptor exactly, and only that molecule could fit into the receptor, and that would make you smell. That's the lock and key model of olfaction. The problem with this model is that we have 390 about types of receptors, but we can smell 10,000 smells. So we can't have a receptor for each smell, because there are simply not enough receptors. And they also found that molecules with more or less the same size, same shape, gave different smells, but molecules with different shapes often had the same smell. There was also a partial lock and key model, that perhaps the key part that fits into this receptor is perhaps just a functional group. But there's also some problems with this hypothesis, and that's that different arrangements of functional groups smell differently. So this molecule, vanillin, that is vanilla, has the same functional groups as isovanillin, that smells like hospital apparently. But even though they have the same functional groups, so they should have the same keys, they smell differently. So there is also the quantum involving hypothesis that these receptors, in order for these receptors, the gray structure, to work, an electron has to pass within the receptor from a donor to an acceptor state. And perhaps these molecules, the oscillations in the odorant, that's the molecule that you smell, the perfume molecule, say, perhaps oscillations in the perfume molecule can facilitate the transfer of electrons from the donor state of the receptor to the acceptor state. And this involves quantum tunneling of the electron. So there's where the quantumness comes in. There's some, it's not clear whether this hypothesis is correct, obviously. There is some indication that that the vibrations are involved, for instance, when they replace hydrogen with deuterium to make the mass of some components of this molecule larger. That would affect the oscillation frequency, and that does seem to affect the smell. But in other experiments, deuteration did not have an effect. So it's still debated on whether this molecule, whether this tunneling mechanism is involved in olfaction. Okay, I'm going to skip the enzyme function. Enzymes, I'll just say something briefly about it. Enzymes are catalysts within your body. They were thought to make the reaction easier, so to lower the potential energy barrier. And that was thought to happen through something called a transition state. The enzyme would then couple the donor and the acceptor in this short-lived transition state. But there were some problems with this hypothesis. So there is also a hypothesis that quantum tunneling of the proton between the donor and the acceptor molecule is what happens in enzyme function, in the function of certain enzymes. Okay, so quantum mechanics in the brain. We heard in Ahsan's talk this idea that quantum mechanics is epistemic somehow. So perhaps the wave function simply represents the knowledge that we have. That's one interpretation of quantum mechanics. The orchestrated objective reduction theory is a bit different. It was developed by Roger Penrose and Stuart Hameroff, and the origins of their theory was introduced in 1989 by in Penrose's book, The Emperor's New Mind. At that stage, I don't think Stuart Hameroff was involved, but he suggested some biological implementation of how this could work. So Penrose based the origin of this hypothesis on the belief that Gödel's incompleteness theorems, there are fascinating YouTube videos on Gödel's incompleteness theorems. I would really encourage you to look at them. But Gödel's incompleteness theorems basically say that there are some mathematical truths that we can't prove. In other words, there are some mathematical facts that are true, but which we cannot compute. Roger Penrose says that our brains can sort of understand those mathematical facts. Maybe I'm misrepresenting his view a bit. But based on Gödel's incompleteness theorems, Roger Penrose made the hypothesis that the brain is not a sophisticated computer, or Penrose's belief is that the brain is not just a sophisticated computer, and that consciousness is not purely computational. Penrose and Hameroff suggest that quantum collapse, which cannot be predicted with certainty, so it cannot be calculated, just like Gödel's incompleteness theorems says that one cannot calculate everything. Penrose and Hameroff suggest that quantum collapse is integral to consciousness. They also suggest that quantum processes in the brain are orchestrated by structures in the neurons. So the structures that Hameroff proposed are microtubules. You have many microtubules in your body. They give a skeleton, the cells, basically. They are prevalent also in neurons. This is a microtubule. You can see that the proteins called tubulins give a rigid structure to microtubules. And these tubulin proteins, of which the microtubules are composed, can be in different configurations, like qubits. They suggest that quantum coherence exists between different tubulant proteins and lasts long enough for quantum computation. And Penrose also thinks that quantum collapse is objective, and it happens. It might happen when enough mass or energy is involved in the microtubules. So there's some gravity linked to gravity as well. But quantum collapse is objective, and the brain can control how and when it occurs. So this is the orchestrated, because the brain controls collapse, objective reduction theory. There are also some proposals to test the conjecture that quantum processes create conscious experience. This is from a Google team. We spoke about it during lunch yesterday. Yeah, so I haven't read the paper in detail. No, you can read it and tell me what you think. Okay. Then I'm very briefly going to, so we looked at quantum processes in biological systems, but we also use quantum mechanics to probe biological systems. So now the quantum mechanics is in the machines or in the mechanisms that we use to probe biological systems. One such an example is MRI scans in medical imaging. Basically, how this works is you have a magnetic field, and due to the Zeeman interaction, there's a split between the different spins of proteins in your body. Not proteins, sorry, protons. So your body is mostly composed of water. Water is H2O. So there's a lot of protons in your body. These protons have spin. When you apply a strong magnetic field, the spins orientate in one direction, given by some, because the energies of these states are different. So they preferentially align in one direction. Then, in an MRI scanner, an oscillating transverse magnetic field is applied. This causes the spin to start processing with the Lambert frequency. You've heard these names in the previous talk as well. And when you take away this transverse oscillating magnetic field, the proton spins relax back to the aligned with the static magnetic field. And you can measure this relaxation back to the static position. That's called free induction decay. It depends on two parameters: spin lattice relaxation and spin relaxation. These spectroscopists might have heard these terms T1 and T2 before. Yeah, but that is different for different types of tissue. And so based on how the spin relaxes back to the equilibrium position, you can get a medical, or you can get an MRI scan. The dynamics are calculated with the Bloch equation. That name you've also heard. By the way, this technique was discovered by Felix Bloch and Edward Purcell. Both of those names, it's fairly common. The Bloch equation is also a name you would have heard during this course. Let me say one last thing that we are currently implementing at my university, University of Pretoria. We want to use a continuous wave laser. So this technique is often done with pulse lasers, which are expensive. So we want to use a continuous wave laser and a nonlinear crystal to create entangled photons. We know that the entangled photons were created at the same time. One of these photons we detect using a very, very fast and very sensitive detector, avalanche photodiode, and the other entangled photon goes to the sample and is absorbed by the sample. Let's say those were FMO complexes in a test tube. these samples then fluoresce after some time, and the fluorescence we detect using another APD. And by determining the time difference between these detections, we can get an idea of how fluorescence decays in time, of the fluorescence lifetime. So we can see how many photons are detected as a function of time. And from that, we can get some idea of the dynamics that take place within the photosynthetic system. Yeah, there's also some technique that called single molecule spectroscopy. Basically, we create a very diluted sample of a fluorophore, something that fluoresces, and we can use such a setup to look at the fluorescence of a single complex, let's say a single FMO complex. So each of these little dots are single complexes. And with such a technique, we can see the fluorescence being shut off and shut. It can be switched off and on again. That's called fluorescence blinking, which is also seen in quantum dots. But our group, Neill, Towan, and some others, showed that this on and off switching can be controlled, and that can be used by photosynthetic systems to switch themselves off in order to prevent damage under high light conditions. Okay, so now let me start on the theory. No, yeah, thank you for the organizers of the school, and thank you for listening and attending. By the way, if I'm wrong about any of these stuff, people know more about than I do. Yeah, please let me know.
Yes. Sorry. Oh, I just wanted to understand the application of the Lambert frequency in the MRI scan. Can you maybe say something brief about?
Yeah. So I don't know the detail exactly, but you have all of the spins in water molecules, in the hydrogens of water molecules in your body, pointing in the direction of a. You know that MRI scanners have this very strong magnetic field. That's the scan where you lie in a tunnel and they scan you from top to bottom, and this thing spins, creating a very strong magnetic field. So you have a strong magnetic field and all the spins are aligned to it. Then you create a transverse magnetic field, and this makes the spins precess. And when you take away the transverse magnetic, this precession is at the Lambert frequency. When you take away the transverse electric field, the spins relax back, and that relaxation back gives off electromagnetic radiation that you can detect.
Online, I'm not sure if you can read it, but otherwise it's not reading it.
No, I can't, sorry.
From Tando, to me, he says, with regards to Sir Robert Penrose and Stuart Hameroff's theory, is there another way to interpret the data using a different version of quantum mechanics? Similarly, attempting a similar question, but with the paradigm used being G, the Everettian conception of QM/Bohemian mechanics in formulations.
Yeah, so I think Penrose's and Hameroff's idea was to base this on some biological mechanism. And they have a view that wave function collapse is objective. It's a real thing. The wave function really collapses. And yeah, so collapse is a real thing. I think in the Everettian view, collapse is not real. It's simply that at every point, the Everettian view, as I understand it, is that everything that can happen happens. It's just that you are only in one of those realities. So collapse is not real. It's just that you experience collapse whenever something, whenever you perform a measurement, because the version of you that's in this universe sees only one of those outcomes. So there's not really a biological mechanism attached to that. Yeah, I hope I answered the question.
Okay. Yeah. Is there a mic?
Yeah. Oh, I don't know if it's still online, but yeah, maybe I should perhaps say something since it's the official end of the school, but I don't really know what to say. I'm not so good at informal speeches as Francesco, and unfortunately he's not here. So yeah, I just wanted to finish by saying thanks everybody for coming, especially thanks to all the speakers. Some of them traveled from quite far. So that's hugely appreciated. Yeah, hopefully you enjoyed yourself. Hopefully it wasn't too tiring being here over the weekends. Yeah, and I know that some of you maybe don't have a particularly strong background in some of this content, especially in open systems and things like that. So hopefully the idea of the school was to hopefully make you interested in the topic, and hopefully it has some kind of application in whatever you do. Yeah, I'm not sure if there's anything else to add, but apart from just saying, yeah, thanks for coming, and yeah, hopefully you had a good time. So maybe we can all applaud ourselves for being good participants. Yeah. Okay. Yeah. Yeah. So the idea is to now have the afternoon off to do whatever you want in Stellenbosch. So it's your reward for being so good. But yeah. Okay. Yeah. That's all from me, I think. Yeah. There's still, in principle, lunch should still be there unless I guess it's a little bit after the time we usually have lunch. But yeah, in principle, we have lunch as well. So yeah.